Karthik and welcome to this first video in this series where we are going to talk about Vellum constraints and Vellum simulations. So you must know that we can do a lot of things in Vellum. We can do cloth simulations in Vellum, we can do rigid body simulations, simple rigid body simulations, we can do soft body simulations, we can do liquid simulations, we can do even grain simulations in Vellum. So I always recommend people to learn Vellum because if once you understand this, you will be able to pull off a lot of things in Houdini. And for this first video, we are going to look at our first constraint, which is the Vellum Cloth Constraint. And once you understand this, you will be able to do a lot of things in Houdini because cloth constraint is a very powerful constraint. So let's have a look at this. If I come to this middle example here, the first example here, and if I play this, you will see that we have a very simple Vellum cloth simulation. Okay, we have a grid here or a cloth here, and we want this to behave like a cloth. Okay, so basically we have a grid here, and I wanted this grid to behave like a cloth. Okay, so I provided this grid with some cloth-like properties. Okay. This is the grid. I want it to behave like a cloth. So I provided this grid with cloth-like properties. Okay. And then I connected it with our Vellum solver and I connected it with a collider. And when I run it, I am getting this result. This is it. The simple grid we have here, I provided it with some cloth properties and then I applied some gravity on this and it is falling down and it is colliding with our tube. And this is a simple example, okay? But it shows you how the Vellum actually works. And this will work for anything. So basically, first we have a geometry, okay? And in this case, we have a grid here. And I wanted this grid to perform like a cloth. So I provided this grid with the desired properties, cloth-like properties, okay? And then I connected it with our Vellum solver and I ran it. Similarly, if you want a balloon or if you want a sphere and you want it to behave like you want that sphere to behave like a softball or you want that sphere to behave like a balloon, then you will give that sphere some balloon-like properties, connect it with our Vellum solver and it will do its magic. So let's first focus on this, okay? This is the basic formula. Your geometry, apply it with some properties and then connect it with solver. And to apply those properties, we use constraints, okay? By properties, what I mean here is constraints. How this grid needs to behave, we define that with the help of our constraints. We are basically providing some properties here to this grid. So let's start with this example only and I think you will better understand it. So if I come here and if I run this simulation again, you will see pretty simple solution. A grid behaving like a cloth colliding with our object. And how do we create this? So it's a very basic formula. As I said, we have a grid here, we have our geometry here, and I want this geometry to behave like a cloth. So what will I do? I'll provide it with some cloth-like properties, and I can provide it with cloth-like properties with the help of a constraint. Okay. So in Houdini, if you create a Vellum constraint node, as I said, this is a Vellum constraint node, and if you come to the constraint type, then there is a lot of constraints here. There's distance, cloth, hair, string, pin to target, attach, geometry, pressure, glue, struts, a lot of things, shape match, a lot of things, okay? And you can create hairs here, you can create cloth, you can create RBD, rigid bodies with a shape match, struts and glues and a lot of things, a pressure with you can create balloons with pressure, a lot of things, okay? And what kind of property you want to give your mesh is decided with the help of this constraint type, okay? and this is it. You can create a lot of constraints, and here you decide what you actually want to create. In this case, we want to create a cloth. Okay, so you can create a vellum constraint and then change it to cloth. Okay, something like this, or you can create a already pre-configured node here, which is called Vellum Cloth Constraint, Vellum Cloth Configuration. So this is a configuration which is already figured by Houdini, and they have done all the necessary things here, and you would not have to change a lot of things here for your simulation to work. Okay, so I always prefer to create a vellum cloth, or I always prefer to use the pre-configured setups here. So for vellum cloth, you can just press tab and create a vellum cloth configuration here. Okay, and this is the configuration that I've used here as well. Now let's see. As I said, we have a grid. I want this to behave like a cloth, so I will apply some cloth like properties, and I will use Vellum Cloth Constraint here to apply those properties, or to give those properties to our grid here. Okay, so if I come here, you will see that this Vellum Cloth Constraint is taking 3 inputs. The first is the vellum geometry. What geometry do you want to to apply the properties to? This is our geometry. Connect it here. Do you have any existing constraint? We don't have it. Do you have any collider that you want to use in the simulation? Yes, we do have a collider, which is the tube here. This is our cloth and this is our tube. And I have made some changes here with the help of a poly bevel. But this is our tube, this is our collider that we want our cloth to collide with, and we will connect it here. Now, once we have connected our geometry and we have connected our collider with our Vellum Cloth Constraint, you can see that we have 3 outputs here. The first is our geometry. You can see this is the geometry that we are putting in. So after this grid, I have created a remesh to provide some details here. Okay, so that we have enough points for our simulation, and I have connected this remesh here, and if I take it out, I am getting the same geometry here. Okay, with some extra attributes, which is drag normal, some applied mass here, we have some p scale, and we have some velocity as well. Okay, so this is the geometry that we are getting out, which is look wise, geometrically wise, it is looking the same as our input here. The second thing that we are getting here is, I'll create a null, I'll connect it with our middle output, which is the constraint geometry. Let's name it cons, and if I visualize this, you will see that we are getting this constraints here, and these constraints are lines between the points here. Okay, so we have these points here, these points, we have these 4 points, and the constraints are applied between these points. You will see this is a constant, this is a constant. The lines between all these points are basically the cloth constraint. Okay, and that is what we are getting. So what does this constant actually do? This basically provide the cloth properties, but what cloth properties are we providing here? If you come to the Vellum Cloth Constraint, and if you go down here, this is our Vellum Cloth Constraint, go down, and you will see here 2 sections, 2 important sections actually. The one is the stretch section. Okay, this is the stretch section, and the other is the bend section. For specifically for cloth configuration, for cloth simulation, we are using our Vellum Cloth Constraint to provide this geometry, to provide this grid with 2 important cloth properties. Okay, and what are those properties? We are deciding, we are providing how stretchable this cloth is going to be. Okay, how stretchy the cloth is. Is it like elastic? Is it going to be too stretchy? or is it going to be like normal cotton, like it's not going to be very stretchy but it's going to have some stretchy property, or is it going to be like a leather which essentially does not have any kind of stretchiness, any kind of stretch power. It has low stretch properties. So what kind of stretchability do you want this cloth? What kind of stretchability do you want this cloth to have? Do you want it to have a normal stretchability like cotton? Do you want it to be very stretchable like elastic? Or do you want it to be not stretchy at all like leather? This stretch section decides that. Okay, we control how stretchable the cloth is going to be. The second thing is bendability. How bendable the cloth is going to be. Bendable means foldable. You have seen cloth, you must have seen a handkerchief, you must have used it. A cotton handkerchief is very foldable. You can fold it as many times as you want, and then you can keep it in your pocket. But let's say that you do not want you do not want this grid, or you do not want this cloth to have very foldable property. Okay, you want it to behave like a leather, and leather is not very foldable. If it's a very heavy leather, then it's not going to be very it's going to have a less folding capacity than a cotton cloth. Okay, and we decide the bendability and the foldability of an object or the mesh from this section. How foldable the object is going to be, or how bendable the object is going to be, this is where we decide that. Okay, so basically the cloth constant, as I said, is providing our object or grid with two important cloth properties. One is how stretchable it is going to be, and the second is how foldable it is going to be. Okay, now if I come to the stretch section here, you will see that there are a lot of properties here. To define how stretchable the cloth is going to be or how unstretchable the cloth is going to be, we need to play with this value, the stiffness value. If the stretch stiffness is very high, it says that the cloth is not going to be very stretchy. Okay, let me just create a note here. If the stretch stiffness is very high, then the cloth is not going to be very stretchable. Okay, if the stretch stiffness is very high, then the cloth is not going to be very stretchable. If the stretch stiffness is very low, then the cloth will be very stretchable. It's going to be very stretchy. Okay, if the stretch stiffness is very low, the cloth will be very stretchy. Okay, if the stretch stiffness, if it is stiffness, basically means, think of it as strictness. Okay, how strict are we in providing stretchability or stretch properties to this cloth? If you do not want it, then you have to be very strict and then increase the property. Okay, increase the stretch stiffness. If you want it to be very stretchy, then we will have to be very lenient, just decrease the stretch stiffness here. If you want it somewhere between, then you can create the stiffness in the middle here. Okay, so basically if the stretch stiffness is very high, cloth is going to be not very stretchy. It's not going to allow stretchability very much. If the stretch stiffness is very low, then the cloth is going to be very stretchy, and you need to find a optimal balance here for your cloth if you want it to behave certainly with certain properties. Okay, so stretch stiffness decides how stretchable the cloth is going to be. Similarly, in the bend section, the bend stiffness decides how bendable or how foldable the cloth is going to be. Okay, if the bend stiffness is very high, then the object or the cloth is not going to be very bendy. If the bend stiffness is very low, then the object or cloth will be very bendy or very foldable. you need to find optimal value here as well for your object as per your requirement. Okay, so this is that. This is the stretch section, controls how stretchable the cloth is going to be. This is the bend section, controls how bendable the cloth is going to be. And stretch stiffness decides the main value, which is how stretchable the cloth is going to be. And bend stiffness here decides the main value, which is how bendable or foldable the cloth is going to be. Okay. This wrestling scale, compression, stiffness and damping ratio and everything else we'll talk about in future chapters. So just keep in mind this, that the Vellum Cloth Constraint gives our cloth or our grid or our object with cloth like properties, and the two important cloth properties that we are providing here is how stretchable the cloth is going to be. I'll just write it here for you. Vellum Cloth Constraint provides with two important cloth properties: how stretchable and how bendable or foldable the object is going to be. Okay, I hope this is very clear, because it's a very simple concept and I have tried to explain it to you in a very simple terms. I'll just read it once again, or actually I will just go through it once again. We have our grid here. This is our grid, or this is our grid. We want this grid to behave like a cloth, so we applied some cloth properties. How did we do that? We used Vellum Cloth Constraint to give this grid some cloth properties. And the two important properties of cloth that we provided this grid with the help of Vellum Cloth Constraint are stretchability, how stretchable this cloth is going to be, and bendability, how bendable or how foldable the cloth is going to be. Okay, this is what we have done. We use Vellum Cloth Constraint, which has provided this grid with some cloth properties, and we control those properties, the main stretchable property and the bendable property, in this stretch section and the bend section. Now, after I have applied Vellum Cloth Constraint, I can connect the Vellum geometry. I can create a Vellum solver. Okay. Create a Vellum solver. This is a Vellum solver similar to this, and I can connect this geometry here in the first geometry. I can connect this constraint here in the second required constraint input, and this output for collider should go in the third collision. You can hover over this and you can see that what these inputs and outputs are exporting or importing. Okay, and once we have done that, we can come to our Vellum solver, and you will see that we can visualize our collision here. And if I play this, just default, there's nothing that I have changed here. We are getting this result. Okay, this is our first Vellum Cloth Constraint. Okay, and in the Vellum solver there are a lot of things that you can do, but we will learn each of them one by one as we progress. Okay, in the solver we have a lot of settings. The first is full or minimal, and solver mode full is quite good for our Vellum cloth simulation. I actually required the full version for our cloth simulation, or any kind of cloth simulation, any kind of simulation which involves cloth, just use full. Okay, substeps basically increase the calculation time between each frame. Okay, and if you want a more accurate or a better simulation, if you are feeling that I'm not getting a very accurate result, then you can increase the amount of substeps here and then press the simulation here. Okay, then you can play the simulation. The only downfall is that if you increase the substeps, then the simulation time will increase. Okay, as the calculation is obviously increased per frame. If I make it 5, then every frame I have asked the Vellum solver to calculate the simulation 5 times every frame. Okay, that's basically it. Now, the constraint iteration is the same thing as substeps, but it is only working for the cloth constraint. Okay, if you are feeling that our constraints are not working fine, and then you can probably increase the constraint iteration. But I will ask you to only use substeps. Do not use this. We will maybe use this in advanced things, but initially you do not need to do this. If you want to improve your calculations, if you want to improve your simulation, if you are getting any problem, then just increase the substeps here. Okay, then in the collisions, we have enabled the collisions and self collisions as well, which means controls if self collisions are detected. Let's say that this cloth somehow collide with itself, then also it's going to happen. And then we have ground plane here. Okay, so ground plane is basically the ground area, and if I run this simulation now, you will see that this is not only colliding with our tube, but it is also colliding with our ground. Okay, you can turn this off for this one. And similarly, there are a lot of things. If you come to the forces, you will see that gravity is applied by default. Gravity is a force which is minus 9.8 applied in the negative y direction. We have built-in wind. You can apply some wind if you want. And there are a lot of things here, but we do not need to care about this about them for the first constant or first example here. Okay, so this is basically what we have done. We have created a geometry. We wanted this to behave like a cloth, and now we have done it. So this is the first simulation, cloth simulation here. Okay, congratulations if you have followed along, and this is your first Vellum simulation. After the Vellum solver, what you can do is create a Vellum post process here. Okay, and the Vellum post process, what it does is basically we can provide some extra detail to our cloth object. Okay, so maybe if you want to provide some more points here, then you can create a loop here, and it is creating subdivision here after the simulation. Okay, we can also create thickness here. We can extrude the cloth here, and if the cloth is detangled somehow, you can do that here as well. You can also provide some spatial blur, but we will look into all of this later. For now, if you want to create subdivision, you can do, but I am not doing any of that. After that, I have created a color node here and provided that color. I have taken my collider here and I have connected both of them. Now if I play this, you can see the simple cloth constraint or simple cloth simulation is working pretty fine. So this was the example 1, and now let's look at other examples here. Okay, so before we move on to our next example, I wanted to show you something else as well. Other than the two properties that controls how stretchable the object is going to be and how bendable the object is going to be, we have one more thing that controls how our simulation is going to behave or how our object is going to behave, and that is the resolution of our geometry. Okay, in this case, initially I had a grid and there are only 4 points here. There are only 4 points here. You will see we have 4 points here. This is the single face. Then I have done a remesh. I've used a remesh node to create a detailed geometry here, to create a geometry with higher resolution. So there are a lot more points here. You will see there are almost 4,000 points here. Okay, and that makes this geometry a very detailed geometry. And this is very important because when we say that we have created this stretch property and bend property. What we are basically doing, stretch property and bend property for this mesh, what we are basically doing is we are defining the stretchability and bendability between the points here. Okay, these constant here are formed between the points here. So we have these 4 points here, and the constants that we are getting, the stretch constants and the bend constant, these are the relationship between these points. Okay, so when I'm saying that we have given a specific stretch value, then we are basically defining how stretchy, or what is the stretch value going to be between these 2 points. How is the relation between stretch relationship between these 2 points is going to be. That's what we are deciding. Similarly with bendability or foldability as well. When we are deciding how bendable the object is going to be here in the bend section, we are basically defining the relationship, the bend or fold relationship between these between 2 points. Okay, so now let's move on to the second example here, which is the flag example. And we are going to follow the same things that we had done in the first example. We have a grid here, and we want this grid to behave like a cloth, certainly like a flag. Okay, and then there's only one change here that we had done. In the past example, in the first example, we had the cloth here, okay, but it was just instantly falling down because of the gravity. There was no part of this cloth which was hanging up or which was pinned. But in this example, while the flag is moving, while the geometry, this mesh is moving like a flag, like a cloth, there's part of this geometry, this area, these points here, which are pinned. And they are pinned, which means they are going to stay in their original position and they are not going to take participation in the simulation. Okay, and we will learn in this example how we will do that, how we can pin certain points or certain geometry in a mesh which will not take participation in the simulation, which will just stay in its original position. It will not move in the simulation. Okay, so let's look at that. We have a grid here. Okay, this is our grid. Then you will see that there are only 4 points here. There's not enough geometry here for this grid to behave like a cloth. So we are gonna apply a remesh here. Okay, and if I just turn the smooth wire shaded, you will see that now we have enough geometry. Okay, this will behave like a cloth once we have applied our Vellum constraints here. Okay, so we want this to behave like a cloth. So after this, we can create our Vellum Cloth Constraint. And I have not changed anything here. It is just the default Vellum Cloth configuration. You can press tab and create a Vellum Cloth configuration here. Okay, the only thing that I have done here is I have, above the stretch section, I have come to the pin to animation section here. Okay, and in this section what we can do is, let's say that after the remesh I have created a group. Okay, and in this group, this is a point group and I have named this group to be pin, and in this group I have selected these points here. Okay, I have selected these points in my base group, all these points, and once I have selected these points in this group, I'll come to our Vellum Cloth Constraint, I'll come to our pin to animation, and then I will pin all these points which are in this group called pin. So basically, once we have pinned any point, that point is going to stay in its original position. It's not going to move, it's not going to simulate, it's not going to take participation in this Vellum simulation. Okay, and that's what we are basically doing here. We have pinned the points here. Which points? The points which are present in the group called pin. Okay, and these points will not take participation in the simulation. Everything else will behave like a cloth except these points. Okay, and that's what we have done with the help of the pin points here. Now if I play this, Why is this? Let me just. Okay. Now, if I play this solver, if I run this simulation, you will see that all the points here, the rest of the mesh is behaving like a cloth, okay, as expected. But the points that we have selected for our pin, which are selected as pinned points, they are not taking participation in the simulation. They are holding their original position. And that's what the pin points here do. The pin to animation section does here. Okay, that's what we do with the help of this pin points. We select a group of points and then we put the group here, and those points which are in this group, they will not take participation in the simulation. Okay, they will just hold their original position. So this was the second example. In this example, inside of a Vellum solver, I have also used a pop wind, and I have used some vex here so that we have a variable wind velocity, and we can have that cloth-like effect here. Okay. And after that, I have connected a pole here, and this is looking like a flag. So now we have learned two important things in Vellum. The one is how we can give properties of cloth to any geometry, like in this example. Okay, this was our grid, and then we provided our Vellum cloth properties with the help of our Vellum Cloth Constraint. In the second example, we learned that if you want any specific points to not participate in the simulation, then you can come to the pin to animation section and we can pin those points. And once we have pinned those points, they will just stay in their original position and not participate in the simulation. Okay. And this is our second example. You can see. So we have learned the Vellum constraints, how to give properties of cloth to our mesh. Then we have learned about the pin points, which basically do not participate in the simulation. They hold their original position. They are pinned to their original position. And now another example is this one. Everyone, so this is the third example, and you will see that this example is pretty similar to the first example. The only difference is that in this example we are constantly emitting this cloth, which is then getting affected by gravity, and then it is colliding with our collider here. Okay, so we will learn about constantly emitting Vellum objects in this example, which is also one of the basic things that you need to know. So let's look at this setup. So I have here a grid. Okay, this is a grid with 4 points here, and then I have used a remesh node to provide it with some good amount of geometry, good amount of points here. This is a high definition grid now, and then I have used a Vellum Cloth Constraint here, which will give me the geo and the constraint, which I have nulled out here. Okay, I've used a null here to define them, and then I have connected them to our Vellum solver. Now, how can we constantly emit our geometry that we are getting and the constants that we are getting here? We will do that with the help of a node called Vellum source node. Okay, and that node can only be created inside our Vellum solver. So if you go inside of a Vellum solver, you will see that I have used a Vellum source node. Okay, so you can create that by pressing tab, Vellum source. This is the node that I'm using, and I have connected this node to our source here. Okay, so if I connect a new Vellum source and if I play this, we will be only getting one cloth here. We will not be emitting cloth because we have connected our geometry here and our constant here. But to constantly emit, we need to change some settings here. So this Vellum source is used for a lot of things. If you come to the emission type, you will see that we have a only once option. Okay, And then we have each frame option, each substep option, and instance on points option. The only once option works just like this. You will use the Vellum object and Vellum constraint, and when you play the simulation, it will, the only object that is put inside of a Vellum solver will be simulated. There will not be constant emission of the cloth object here. But if I change it to each frame, and then I will have to provide which object do I want to produce or emit each frame. Okay, and then what we can do in the swap path and in the constant swap path, we will put those values. So this is our geometry. I'll copy this and I'll put this path inside our Vellum swap path. Okay, and for our constant path, I'll copy this constant, and in the path here, I'll put this constant swap path. Now if I play this, you will see that a cloth object or our geometry that we have defined earlier is getting emitted each frame. Okay, it is getting emitted each frame, and this is how you can do constant emission. If you do this on every frame, you will emit a cloth like geometry here that you have defined outside, or that you have defined here. Okay, but in my example, what I have done is I have asked, or I have put a code here inside our Vellum source, and I am asking it to only emit our geometry every 8th frame. So now if I play this, you will see on first frame, then on 8th frame, then on 16th frame, then on 24th, 32, so on and so forth. So what I'm asking is basically you have to emit an object on the multiples of 8. So emit an object on the first frame, then emit an object on 8th frame, then emit an object on 16th and 24th and 32. And I've used a code for this. So as you can see, we have activation here. So what activation basically does is, if I connect over this one, so when I say that activation is 1, it means that this node is active. We will be sourcing our object when this is active. And activation is 0 means this node is not working. This node is disabled basically. Okay, it's not working. And with the help of this activation, we can code here on what frame do we want this node to be active and on what frame we want this to be inactive. And we can do that. Let's say if I say if at the frame is divided by 10, is modulo by 10, and the remainder is 0, which means any frame which is divided or modulo by 10 and the answer is 0, then which means modulo means remainder. So if I divide 2 by 2, then the remainder is going to be 0. But if I divide 3 by 2, then the remainder is going to be 1. So what I am basically asking here with the help of this code is, on any frame, look at this first frame or 10th frame, if it is divisible by 10 and the remainder is 0, then you need to activate this node on that frame. Okay, so if I run this, you will see on 10th frame this will get activated. On 20th frame this will activate again, and that's why we are emitting it on the first frame. Then after that we are emitting on the 10th frame, and after that we are emitting on the 20th frame, and so on and so forth. Any frame that is divisible by 10 and the remainder is 0, then on that frame turn this node on. That's what we are basically saying here. Okay, so if I play this whole, you will see on 10th, then it will get activated on 30th because 30 is divided by 10 and the remainder is going to be 0 for that. 40 is obviously divided by 10, remainder is going to be 0, then on 50 and 60 and so on and so forth. In my original Vellum source, I have used my code a little differently. I have asked this Vellum source to get activated on every 8th frame. So we can do that here as well. If you come to the Vellum source and change the code from, and just to get this code, you have to press it once. You have to left click it once with your mouse, and you will get this code. So @frame modulo 8 is equal to 0. Then you will see that on the first frame it is going to get emitted, and after that every 8th frame. So on frame 8, on frame 16, 24 and so on and so forth. So you can decide here what frame do you want it. The modulo needs to be 0, just keep in mind. So if I put it 15, I'm just giving another example. On first frame this will emit, and then after first frame it will emit on every 15th frame. 15, 30, 45, 60, so on and so forth. Okay, but let's just keep it at 8. So any frame number which is divided by 8 and modulo or the remainder is 0, then this Vellum source should be activated on that frame. Okay, and we do not want to emit on any frame higher than 55. So we can use another code here, and to write another code we can press double and this symbol 2 times, and then we will write @frame any frame which is less than 55. So what we are basically saying here is this activation should be only active when the frame is divisible by 8 and the remainder is 0, and it should be only activate on any frame which is less than 55. Okay, so the conditions that we have given here are: turn this activation to 1, turn this node on when the frame is divisible by 8 and the remainder is 0, and the other condition is the frame should be less than 55. So 8 times is 64. Okay, so if I run this, you will see there's that any frame that is divisible by 8, this will get turned on, but after frame 55, even if the frame is divisible by 8, it will not turn on. So we have put on 2 conditions here. So after 55, even if it was a frame which is divisible by 8, it will not get activated. So 56 any frame which is higher than 55, it's not getting activated. Okay, even if it is divisible by 8. So this is the code that we have written. So basically what we have done here is to constantly emit, we will have to create a Vellum source node, and then we can create it, we can set it, the emission type needs to be each frame. We will have to give the SOP path for the geometry and the SOP path for our constraint here, and then we can write the code here on which frame or how long do we want the emission to be. In this case, we want the emission to be on every 8th frame, and we do not want the emission to happen after the frame 55. Okay, so this is the third example. After that, after the simulation, what I have done is I have used a Vellum post process. I have not done anything here. I have used a assemble node because once the simulation is done, I want to give attribute to each of this cloth emission, the emitted cloth that we have created. So there are almost 7, exactly 7 cloth here. 1, 2, 3, 4, 5, 6, 7. Okay, and I wanted to give name to each of this cloth here, and with the help of that name attribute, I have used a color node here, and the class is primitive because the name is primitive class. I have used the name attribute here to randomly color these cloth. Okay, and then I have just used a merge node, and this is the example third. So if I look at all three examples now that I have taught you, this is what we are getting. This was the first example where we learned how the cloth simulation actually works. We have a grid. We give that grid some cloth properties, which is called constraints in Houdini, and then we connect it with our Vellum solver. Some gravity is applied and it is colliding. Here also we used the same method, but we learned another thing, which is pinpoints. So in our geometry here, we can decide which of the points should participate in the simulation and which of the points can be pinned to their original position, which means they will not participate in the simulation. They will stick to their original position. Okay, they will not move. In the third example, we learned about continuous cloth emission or continuous object emission in Vellum, and we do that with the help of our Vellum source inside our Vellum object, Vellum solver, and we will have to provide some swap path to our geometry and our constants, and then we have to decide on which frame do we want the emission to happen. Okay, so these are the first three examples of this series, and these are the examples of the cloth constraint geometry. So I hope you learned something from it, and we are going to cover a lot more constraints here in the next 10 days, in the next 10 videos. So I hope you learned something from it, and okay, so we can move on to our next configuration or next Vellum constant, which is the pressure constraint, or as you popularly known as Vellum Balloon Configuration. Okay, so here you can see two examples. One, we have emitter. We are emitting spheres here which are behaving like soft body objects, like a balloon, if I can say so. And this is one example. Okay, the second one is this example where we have a test geometry. It is falling down. It is behaving like a balloon. It has some kind of pressure inside this. Okay, as you can see, and we have a collider here. So when this collider is pressing this object or geometry, when this part is being pressed, you will see that the pressure which was here is transferred to the rest of the geometry. Okay, and this is behaving quite like balloon. Imagine if you had a balloon which was shaped like this object. If you press it from this side, the pressure or the air will transfer to the rest of the object and it will inflate that better. So this is basically what we are getting. Okay, so before we go through these examples, I'll just give you a basics of Vellum balloon configuration, and let me create a geometry network for that. I'll call it example, and let's go inside. I'll create a sphere here. This is a sphere. Let me just visualize this properly with smooth wire shaded. Let me create the grid here. Okay, we have a sphere here. I'll change the primitive type to polygon. I'll increase the frequency to 10, and I'll move it in the y direction by 2.5 meters, something like this. And now if I create a Vellum Cloth Constraint for this sphere, you will see that we will be applying the two important cloth properties as we have already discussed, which are the stretchiness and the bendiness, and it will fall down and it will behave like a cloth. Okay, so let's see if that will work. I'll create a Vellum Cloth Constraint. After that, I'll create a Vellum solver. Press Vellum solver. Let's connect the geo to geo, constant to constant, and the collider to collider. In the Vellum solver, I'll create a ground here, okay? And now if I run this simulation without changing any kind of settings, okay? If we come to the Vellum Cloth Constraint, we have applied the stretch stiffness, which is quite high, 1e plus 10, which basically is saying that we do not want it to be very stretchy. And then we have bend stiffness here, which is reasonably low, which means that we are allowing this object to have some kind of foldiness or bendable properties, okay? And this is behaving exactly like a cloth. This is a cloth which is shaped in sphere, and there's nothing inside it. So if I play this, it will just crumble like this, okay? Working perfectly fine. But what if this was a balloon, okay? And we know that a balloon is, if it is a air balloon, then it will be filled with air, and that air is trying to expand, okay? And thus creating a pressure inside this balloon, which makes that balloon to keep its shape, okay? What if it's a water balloon? The water inside the balloon will also keep some amount of pressure inside, okay? So that the sphere will not crumble, okay? Because it is filled with water. So if I create a pressure like substance, if we create pressure on this sphere from the inside, then what we can do is we can make sure that the sphere tries to keep its own shape. It can become a little bendy and it can stretch a bit, and it will behave like a soft body, but it will mostly try to keep its own shape, okay? And we can do that by creating a pressure inside the sphere. And in Vellum, we can create pressure with the help of pressure constraint, okay? So if I create a constant called Vellum pressure, we will not have any, but I can create a Vellum constant. I can create a Vellum constant, and in Vellum constant we can change the constant type to pressure, and then we can connect it here, okay? And if I play this, let's see what will happen. You will see that this sphere is now has some kind of pressure inside it, and that's why it is not crumbling like before, okay? It's behaving like a soft body, okay? But instead of creating the Vellum cloth and the Vellum constant, pressure constant separately, what we can do is we can create a Vellum balloon configuration, which is a combination of these two constants. So just press tab and create a Vellum balloon configuration, okay? And now if I just connect this sphere here, and if I connect the last output to the input of the Vellum solver, and if I play this, we will be getting a similar result, something like this. In this case, it's just too squishy or too soft body, okay? This is what we are getting. And we are getting that result because of these two constants. The one is the cloth constant, and we saw it working in the previous example also, and here also. This is creating the two important properties of cloth, which is the stretch stiffness and the bend stiffness. Because we have created a balloon configuration, it has been given a value here for the stretch stiffness, which is 6 into 100, which is quite low, okay? This stiffness is basically saying that this object can be very stretchy, and we can see the result here. Because the object is very stretchy, this is how it is behaving, okay? If I increase the stretch stiffness to 1e plus 10, which is the highest, that basically means that we do not want this to be very stretchable, okay? And if I play this now, we'll see this is what we are getting, okay? So we can control how stretchy or how stretchable or how bendable this object is going to be, even if there's some pressure inside it, okay? If I keep it at 1, you can see that it's quite stretchy, okay? So I'll just keep it at the highest 1e plus 10. We do not want it to be very stretchy. We can also control the bendiness here. So basically 0.1 is the bend stiffness here. Basically we are saying that we do not want it to be very bendy and we do not want it to be to not bend at all. So it is somewhere in between 0.1. Okay. And if I play this now, you will see obviously this is what we are getting. So this is how the stretch stiffness and the bend stiffness work in the balloon settings here. Okay. But we need to know how to control the pressure inside this balloon. Okay. How the pressure is controlled and how the pressure is maintained inside this sphere. We can do that with the help of the Vellum constraint, Vellum pressure constraint. Okay. So in Vellum pressure constraint, you will see unlike the cloth constraint, we do not have the stretch stiffness and the bend stiffness. We only have one kind of stiffness here. Okay. We only control we do not have the two sections here, which is the bend stretch section and the bend section. We only have one kind of section here, which is the stretch section. Okay. And this stretch section is not similar to the stretch section in the cloth. Okay. So I'll give you one hint and I'll give you one important factor that you need to remember in all of the constants here in Houdini, Vellum constants in Houdini. The stretch stiffness and bend stiffness does not mean the same thing in every Vellum constant. Okay. Remember this. The stretch stiffness and the bend stiffness does not mean the same thing in every Vellum constant. Okay. So we have a lot of constants. We have cloth constant, we have hair, we have string, we have pressure. And the meaning of the stretch stiffness in cloth constant is that we are controlling how stretchable it is going to be. The meaning of the bend stiffness in the cloth constant is how bendable the cloth is going to be. But in the pressure constant, it means completely different thing. First of all, we only have stretch section, and here also the stretch stiffness is not the same as the cloth constant stretch stiffness. Okay. With the help of the stretch stiffness here, we are controlling or maintaining the pressure inside the sphere. Okay. If the constant type is pressure and I'm playing with the stretch stiffness, then here we are controlling the pressure. Okay. We are maintaining the pressure inside here. Okay. And that's what I'm trying to say here. The stretch stiffness and bend stiffness does not mean the same thing in every Vellum constant. Stretch stiffness and bend stiffness will mean entirely different things in different constants here. Okay, so I'll just change it to default, which was the cloth. I'll just press Ctrl Z and we have our cloth constant here. Okay, so if you come to the Vellum pressure constant, we only have the stretch section here. Okay, and this stretch section only controls the pressure, how we are going to control the pressure inside the sphere, and whether we can increase or decrease the pressure inside the sphere. Okay, so I'll just tell you, the stretch stiffness controls or maintains the pressure inside the object. Okay, this basically is trying to control the pressure or maintain the pressure inside the sphere. So we have, let's say that this was a sphere, and we have given pressure inside this. To maintain the same amount of pressure throughout this simulation, we are working with this stiffness. Okay, we have the stiffness to maintain the pressure inside the sphere. So if I play this with a very high stiffness setting, this is what we are getting. Okay, if I decrease the pressure to maybe like 100, you will see this sphere is not able to contain its own shape. Okay, the pressure here is not maintained properly. Okay, so I'm telling you all of this in a very simplistic form So if you come here, the stiffness of the constant which controls how strongly the constant pulls particles back towards its initial rest state. To dial in initial value, change the factor of 20. Okay, so basically, technically, the stretch stiffness controls, this is the initial shape of this sphere, okay? And when we are playing with the stiffness value, the stress stiffness value here, technically what it is trying to do is it's trying to keep its original shape, okay? And in simpler terms, in plain language, what I'm trying to tell you is the stretch stiffness here controls the pressure, okay? If the pressure is very high, then it will try to maintain its original shape. If the pressure is very low, then you will see it cannot maintain its original shape. This will behave like, because the pressure is not maintained properly here. Okay, so I'll just keep it at 100. And if I play this, you can see that the pressure is not able to maintain the shape of the sphere properly. If I keep it at very high, it will behave like a soft body, but at least the shape is a little better, okay? So this is used to maintain the pressure inside the object. But what if we want to increase the pressure? What if we want to increase the pressure of the sphere? We do that with the help of the rest length scale, okay? Stretch stiffness maintains the pressure, and rest length scale increases or decreases the amount of pressure inside the sphere, okay? With the help of the rest length scale, we decide how much pressure is going to be inside the sphere. And with the help of the stretch stiffness, we are trying to control the amount of pressure, okay? We are trying to maintain that pressure inside the sphere, okay? So I'll just write this here. Rest length scale in plain language increases or decreases the pressure of the object, okay? And these values are applied on the very first frame itself. So if I increase the pressure, if I want to increase the pressure of this sphere, what I can do is I can increase the rest length scale, okay? So if I play this, you'll obviously see that because the pressure is 1.5 times higher, the sphere size will increase. First frame is this, and on the second frame, you will see the sphere size will increase because the pressure is 1.5 times higher. So if I play this again, you will see this sphere has more pressure, okay? And I can similarly decrease the pressure here. So let's say I'll just keep it at 0.99. If I play this, you'll see that we have decreased the pressure, 0.95. Not enough pressure. If I make it 0.8, we'll see we have reduced the pressure even more. If I decrease it like 0.65, we'll see we have decreased the pressure even more, okay? So it's like a football which doesn't really have much air inside it, okay? And you will see the difference now. The pressure that we have given is 0.65 times its original value. So 1 is the default value, okay? And if I make it 0.65, then I have decreased it, okay? But the stretch stiffness is 1e plus 10, which is the highest that we can give here, okay? And it is trying to maintain the pressure which is already given here. So if I play this, the pressure is removed on the first frame itself, and then whatever pressure is left, it tries to, this property tries to maintain or tries to control or maintain that pressure for this sphere, okay? If I keep it at 1, which is the default value, which means the pressure is similar to the volume of the sphere. Okay, we are not decreasing any kind of pressure here. We have just kept the pressure at 1, which is default value. If I play this, you will see this is what we are getting. So this Vellum balloon configuration is a good way for creating soft body simulations, okay, especially like something like balloons. This will work really well. There are other methods to create soft body simulations in Houdini, and we will go through them as well, but this is my favorite because it is very easy to control. Okay, let's just say that you have given good amount of pressure, okay, and you have given enough, you're maintaining you have increased the stiffness to 1e plus 10, which is the highest, and you are trying to maintain that pressure, but still there's some kind of, it is behaving like this, and we do not want that. A football, even though it has pressure inside, it doesn't crumble like this, okay, it doesn't squish like this. What we can do is we can come to the Vellum solver and we can increase the amount of substeps here. So now we are getting a better quality calculation for our simulation. If I press this, you will see that the ball or the sphere is not squishing as much as it was earlier. Okay, if I increase the substeps even more, we will be calculating this even better. So this is a more accurate calculation here. So it is getting squishy, but now we can play our with our value. So if I come to the Vellum bend here, and if I increase the bend stiffness, okay, come to the cloth and increase the bend stiffness, which basically means we are saying that we do not want it to bend very easily or fold very easily. And now if I run this with our high calculation steps, this is what we are getting. It is getting squishy, but the shape is maintained because there's not enough bend properties here, okay. And I can increase the bend stiffness even more, something like this. And you will see now this is behaving like a proper soft body ball. It is getting squishy, but it is not bending very high. The bend properties are not very high here. So when we are doing the Vellum balloon configuration, we are playing with, in the Vellum balloon configuration, we are playing with 4 properties, which is cloth stretchiness, cloth bendiness, maintaining the pressure, and we are increasing and decreasing the pressure inside the object, okay. And I'll copy this. Okay, I cannot copy this, sorry. So okay, so in balloon configuration we have cloth stretchiness, okay, which is cloth stretch stiffness. We have cloth bendiness, and we control that with cloth bend stiffness. We maintain the pressure of the object with the help of pressure stretch stiffness, okay, and we increase or decrease the amount of pressure of the object with the help of pressure rest length scale. Okay, so these are the things that we are using to control our soft bodies in Vellum balloon configuration. Okay, so this was a quick example. I hope you learned something from this, and now we will cover the rest of the examples. Okay, so now we can look at the second example here, which is this one. And it's pretty simple, as I said, and I've already showed you the method that we will be using to constantly emit these objects. Okay, so what we have here, if we run this simulation, is we have spheres which are being continuously emitted, and these spheres are soft bodies. Okay, as you can see, and we have a collider here which is collecting all these spheres. So this is what we will be creating. So let's see what we have. So the first thing that we have is a sphere. As you can see, the sphere is polygon, uniform scale is 1.25 frequency. Then we have used a Vellum balloon configuration. So you can just press tab and create a Vellum balloon configuration like this. Okay, and in this Vellum balloon configuration, I have set the stretch stiffness, which is 100, which is default. The bend is also a default value, and in the pressure, the default value, however, is 100, but I have increased the stiffness here, the pressure stiffness here, to 10,000. So the stretch stiffness for the pressure here is 6 into 10,000. Okay, and I have used a null to output the geometry that we are creating here. Okay, that we are extracting here, and I've also used a null for the constraints. Okay, and these null here output the geometry and the constraints. Okay, and I've named them as well. And then what I've done is I've used a Vellum solver, and this Vellum solver doesn't really have those many features. It's a default Vellum solver. The only thing is that I have connected the geometry here and the constraint here with respect to the geometry and constant, and then inside we have used a Vellum source, as I have told you earlier. Okay, so if I recreate this, it's going to be very simple. I'll just delete this. Let's copy this sphere. Okay, so if I recreate this, I just paste the sphere. This is a sphere. I'm using a Vellum balloon configuration. Okay, this is a Vellum balloon configuration. I have not changed any kind of settings here. And then I'm using a Vellum solver. I'll connect it here, connect all of them, but you will remember that we need to constantly emit our things. Okay, I'll just reset the viewport here. We have not used any collider here as far as this Vellum solver is concerned. So if I use a ground plane and I play this, you will see this sphere is behaving like this with the default values. We need to emit those, so I'll use a null. Let's call it geo01, and you create another null. I'll call it cons01. So this is representing the geo, and this is representing the our constraints. I'll select our Vellum solver. Let's connect our geometry and constraints here. Inside we need to create a Vellum source for continuous emission, and we will follow the same thing that we did in the first cloth constraint example for continuous emission. I'll come to the emission type, change the emission type to each frame. Okay, I'll use our SOP path here, copy the geometry one, and this, let's paste that geometry one path to the SOP path. Come out, copy this cons01. Inside we will paste the path here in the constant SOP, and now what we will be doing here is we will be emitting this spear every frame, but we do not want that. So we can obviously create the formula that we have used earlier. So I wanted to emit every 15th frame. So let's write this formula, which is frame modulo 15, and the remainder should be 0. Okay, which is basically saying that divide every frame by 15, and when you are dividing it, the remainder should be 0. Okay, this is a modulo signal, so we call it modulo. If I press this now, if I run this now, let's see what we are getting. On first frame, on first frame we are getting a spear emission. Then on 15th frame, as per our formula, then on frame 30, then 45, and so on and so forth. So that's what I've done here as well. If you will look at this, then I have created a, let me just reset the viewport. Okay, I have created a spear here, and I've used a box here, and I've used a boolean node. So basically what I'm doing is I'm subtracting the area of this box from the area of this sphere. So this is what we are basically getting. Okay, we are subtracting a minus b. So a is the sphere and b is the box. So this is what we are getting, and I want a bowl like structure basically. So I'm deleting the face here, so I can come here, select this face, and then press enter. So that's what I'm getting, and I'm connecting that object to our collider as collider in our Vellum solver. Now if I play this is what I'm getting. Okay, now the basic thing that I've done here is I've used a Vellum post process. I have used a loop subdivision method here, and I have subdivided the spear by 1, and then I've used a assemble node to give a name attribute to all the geometries that we will be creating. So all these spheres have a different name attribute. I have promoted the name attribute with the help of the attribute promote node. Name is a primitive attribute. I have turned it or converted it into a point attribute, and then I've used a color node. Okay, and I've used a random from attribute, and I've used the name attribute to color all these spheres. So this is what we are getting basically. This was example 1. I hope you understand this because it is pretty simple. This is a combination of the cloth emission that we have done earlier and the recent example of the sphere, Vellum balloon sphere, that I have recently shown. Okay, so this is the example 1. Now let's tackle the example 2, which is this. Okay, so the second example here is this one. As you can see, we have a test geometry here. This test geometry has been given the pressure constraint and the cloth constraint, so it is behaving like a soft body balloon. And I just basically wanted to show you that the pressure here is transferable. What I mean by that is when this is falling down, you can see that this is behaving like a balloon, but when we have a collider here, which is just colliding, and it is pressing down our object here, the pressure is transferring from this part of the object to that part, and this is possible with the help of our balloon configuration. Okay, so this is also a pretty basic example. I'll just show you how I did it. I'll just delete this. So this is our test geometry. This is the test geometry that I have been using. After that, what I have done is I've used a Vellum balloon configuration. Just type Vellum balloon configuration, you will get this. In here, if you come here, you will see that in the Vellum cloth constraint, the stretch stiffness, I have increased it to around 10,000. By default it is 100. I have used 10,000 here so that it is more stiff, which means we do not want it to be very stretchy. And if you come to the bend section, the stiffness is 0.1. okay, and which is default. Okay, so that is that for the cloth. And in the pressure, what I've done here is in the pressure constraint, I have increased the stiffness to 10,000. Okay, and similarly I have connected these combination of the constraint to our Vellum solver. So I'll just show you what I've done here. Let's connect this Vellum balloon configuration to our test geometry. Okay, we have applied both our cloth constraint and our pressure constraint. Let me create a Vellum solver. So this is the Vellum solver, and now what I can do is I can use a ground plane here, and if I play this, you will see this is what I'm getting. But I can improve this result. Basically what I can do is I can ask the cloth constraint to make the cloth less stretchable. So I can come here, come to the cloth constraint, come to the stretch section, increase the stretch stiffness to 10,000. Okay, and now if I play this, let's see what we're getting. The results are not very different, so we can increase the stretch stiffness to maintain the amount of pressure that we have here, because I think it's not maintaining the pressure. So let me just increase it to 10,000, and now this time you can see that it is more inflated than the last time when we simulated this, because I have increased the stretch stiffness, which means that stretch stiffness, as I said, basically controls or maintains the amount of pressure that we have inside here. Okay, in my original I've used these settings, and if you want you can increase the stretch stiffness for the pressure even more, and this is what I'm getting. Okay, now if I want to create a collider, let me create a tube here. Let me just template this. Let me visualize our tube. This is our tube. I'll increase the end caps, increase the number of columns, increase the number of rows as well, 20 something. Okay, and I'll transform this. I'll transform this tube here. So initially let's keep this tube here, and I think we can even rotate this, something like this. Move it closer to our test geometry. I can come to the tube and also increase the height here. So this is what we are getting. And what I will basically do is initially I'll keep the tube here. Okay, so let's create a keyframe here, and on frame 65 I'll just bring it down. Okay, something like this. And if I use this as a collider, let's see what happens. We have already connected our constants here, and I'm connecting this tube here as a collider on the third input, and this will go down on our Vellum solver. So let me run this simulation now. Okay, if I play this, let's see what happens. You will see that as we are applying the pressure here, the pressure from this side of this part of the object is transferring to that part. Okay, you can see, which is a behavior of balloon. So that's what I wanted to show. And in my original example, what I've done here is I kept everything just like this for the object here. For the test geometry, the Vellum constant and the Vellum pressure constant are exactly the same as I've shown you here. In the Vellum solver, I have increased the substeps to 3. Okay, and I have used a ground plane, but the collider that I have used here is a little different. I've used a tube here. Okay, And basically what I've done is I have programmed this tube to move like this. Okay, it will go first there and then it will come back. Okay, so it's behaving like a roller, and that's what I wanted. So I've also given the tube some noise here. Okay, so it is a little bit rough, and after that what I have done basically is I've connected it to our Vellum solver, and then I ran the simulation. So this is what I'm getting. It will go there and it will come back. And it's pretty interesting result if you are looking to do a Vellum balloon configuration or Vellum balloon type of simulation. Then you can do a lot of things, and this was a second example. Okay, all right. After that I have done Vellum post process after the simulation, and I just merge both of these, the collider and the Vellum balloon object. So this is it for the second example as well. So let's move on. Okay everyone, so this is an example of Vellum simulation where we have combined two different kind of constants together. Okay, and it's a pretty simple method, and I'll show you how we can do that, how we can combine any two kinds of constants with each other. Okay, so what I'm gonna do is I'll create a geometry here, geometry network here. I'll just turn this one off. I'll call it example. Okay, and I'll just turn on the grid here. So let's create a grid. Okay, so I've created a grid, and let's decrease the size to 2 by 2, 2 meters by 2 meters. 10 by 10 was too big. I'll also decrease the rows and columns to 2 by 2, and just so you can see it properly, I'll just turn on the smooth wire shaded. Okay, now what I can do is I'll use a remesh node to remesh this geometry properly. As you have already known that for our cloth simulation we need proper geometry on our object. So what I'm going to do is I'll just decrease the target size to 0.05 here, so we have enough geometry. And after that what I basically want is I want the four corners here to just pin on their position, and the rest of the geometry should take participation in the simulation. So I'll create a group. I'll call this group pin. Okay, change the name to pin, and this group type is going to be points. Okay, and in this base group what I'm going to do is just click on this triangle, and then I'll just select some points here. These points, press shift, and these points, press shift, these points, press shift, and select some points here, and then press enter. So what is going to happen is in this base group you will select all those points. We'll see all these points are selected here in this group. Okay, so this is our group now. What I'm going to do now is to give this geometry some cloth properties. I'm going to use Vellum constraint. So we are going to use Vellum constraint node here to give some constraints, cloth constraints here. Sorry, not Vellum constraints, Vellum cloth constraints. So I'll use the Vellum cloth constant here to give some constants to this geometry. Okay, and I'll change the group type to points here, and what I'm gonna do is I'll come to the pin to animation and select our group pin, and these points will be pinned here. Okay, they will not take participation in the simulation, they will hold their original position. In the strut section and bend section I have not done any changes. So what I can do is I can simply create a Vellum solver, and I can connect the nodes here, and then if I play this, you will see this is what I'm getting. Okay, so this is basically our cloth, but this is just one type of cloth simulation that we have done here. What if I want to combine it with other kind of constraints? Maybe I want to create some balloons here which is going to fall here. So what I can do here is I'll use a sphere. Okay, and this sphere is going to be our geometry. I'll just template this. I'll change the perimeter type to polygon. I'll also increase the frequency to 10, and I'll decrease the size uniform scale to 0.5, and let's bring it up here. Okay, and what I can do now is I'll use a Vellum balloon configuration. So these Vellum balloon configuration will give pressure constant and cloth constant to the sphere. Okay, so Vellum balloon configuration, pretty neat. And we have a cloth constraint here and we have a pressure constraint here. And what I can do is I'll just take this Vellum solver and I'll connect this here, move to frame 1, and in this Vellum solver I'll just turn on the ground position. Okay, so if I play this, let's see what we are getting. And we are basically getting a cloth like sphere. There's no pressure inside, because if we come to the pressure strut stiffness which maintains the pressure inside the object is very low. So I'll just increase it to 1e plus 10. And if I come to the Vellum cloth here, the strut stiffness is very low, so I'll just increase it to 1e plus 10, so that strut stiffness is very high. Okay, everything else is okay. I'll run this simulation again, and now you'll see that this sphere is behaving like a balloon. But as I said, we need to combine both of them. So the most convenient method to do this is use a Vellum pack. So what this Vellum pack does is it takes the geometry and takes the constant and it combines them, it packs them in one geometry, and it outputs them like this. So this is one geometry which is packed geometry. Okay, we have points here, primitives, 2 points, 2 primitives, 2 vertices. So these are packed geometry. Okay, what I can do is I can create a Vellum pack here as well for our sphere. This is also packed now. Okay, what I can do is I can combine both of them. So I'll use a merge node, so now they are both combined. Okay, and we need to connect it to our Vellum solver, but we cannot connect it directly like this. We need to unpack them first. So let's create a Vellum unpack node, and with the help of this Vellum unpack we will get our original geometry. Okay, and this geometry is not packed, so you can see that we have primitives, points, vertices, polygons, etc. Now what I can do is I can connect it to our Vellum solver here. Okay, I'll turn on the ground plane, which was our collider, and if I press this now, let's see what we're getting. And now you will see that both of them are interacting with each other. Okay, as you can see, the Vellum sphere is interacting with the cloth here, but this sphere is too heavy. Okay, so what we can do is we can come to our cloth here, and if you go to the geometry section, you will see mass. So mass basically means how heavy it is. Okay, so this is set uniform. So if I decrease this mass, maybe something like 0.001, if I play this, let's see if we are getting a satisfactory result. Okay, so it is not as heavy as in the previous simulation, but we can still improve it. So I'll decrease it to 0.0025, and if I play this now, let's see what we are getting. And now it's behaving properly. We have a sphere which is a soft body simulation, which is behaving like a balloon, and then we have our clothing here, and both of them are working together, both of them are interacting with each other. And this is what we can do with our Vellum pack. And if you need more constants here, maybe you need to add something more, maybe something like a hair constant. So if I create a line here, I'll template this here. So this is our line, and if I go to frame 1, I'll just move this line up something like this, and I'll increase the points to 20, and I'll use a Vellum Hair Configure. Okay, and this will just give the hair properties to this line. I'm going to teach you this later, but I'm just showing you an example. And after this, what I can do is I can Vellum pack this and then merge it here. And now if I play this, you will see that all three of them are interacting with each other, and that's what we wanted. So you can do this with all kinds of Vellum constraints, okay? All kinds of Vellum objects. This will work. This method will work. One thing that I want you to remember is, let's say that you want to separate them later. So after the Vellum solver, I'll use a Vellum post process. Maybe I can run any kind of post process that I want to run here. I don't want to do any here. But what if I want to separate them? I want to spread them separately. So if you have given some kind of group here earlier, so let's say that I'll create a group here, and in this group I'll contain the whole cloth. Okay, so I'll just name this cloth, and when we come to our Vellum Cloth constraint here, come to the geometry, and in the group section here, in the geometry section here, you have a option of where you want to apply all these constraints and all these settings here. So here you can choose our group, which is the cloth. Okay, and this way all these stretch stiffness and bend stiffness and everything, all the settings here will be applied to all the cloth, everything that is within this cloth group. And in here we have selected everything, so these constants will be applied to everything. Similarly, I can create a group here for our sphere. I'll call it sphere, or you can call it balloon, or whatever you want. I'll change the group type to primitive. Just make sure that all the group types are similar. Okay, if one group type is primitive and one group type is points, there can be some problems later. So just make sure that all the group types needs to be same. Okay, when you are creating this group, and when you come to the Vellum Cloth, change the group type to points here and apply it to sphere. Okay, similarly do with our pressure as well. Okay, and now when we are coming out of the Vellum post process, if you want to separate the sphere, or maybe you want to separate the cloth, all you can do is select the sphere and you will get it. And in the split we have our balloon here, and here you will get the cloth. If I untemplate this, yeah, okay, so here you will see only the cloth and the hair sample, and in the other one you will see only the sphere. Okay, with the simulation of course. So this is what we are getting. So this is how you can combine the different kinds of constraints in Vellum, and this is one of the most powerful things about Vellum, that you can combine different kind of things with each other and they all react or interact with each other. That's one of the most powerful things about Vellum. So just use this method a lot and you will get a lot of great results. Okay, I'll see you in the next one. Okay, so we are looking at the third constraint that we are going to deal with, which is the hair constraint. And these are the two examples that we will cover. So you can see that. Let me just cross this one. This is the first example. These are basically lines that I have used, and I have run the hair simulation on those lines. And after that I have given them some geometry. So this is one of the examples. Okay, these are the sort of things that you can do with the help of Vellum hair simulation. And the second example I'll show you here is a pretty basic example. Not so basic, but you'll understand what I'm trying to do here. Just imagine that this is a grass and we have balloon-like things which are moving in the grass, and this is what we are getting. Basically, we have two Vellum configurations here. One is the Vellum Hair Constraint and the other one is the Vellum Balloon configuration, and both of them are interacting with each other. So this is the second example. Okay, so let's get started. Before I show you these examples, I'll just give you a brief overview of what Vellum Hair constants look like. So let's create a geometry network. I'll call it sim. Give it any color you want, and here what I'm gonna do is I'll just create a line. Okay, so when we are doing hair simulation, we are basically trying to simulate lines like hair. Okay, we want these lines, we are gonna create lines with enough geometry. So I'll just increase the number of points to 20 here so that it can properly fold and it can properly bend like hair, and we want these lines to behave like hair. Okay, and as I said earlier also, constraints are basically things that are used to give the properties to the object. Okay, and in this case we have a line and we want this line to behave like a hair, so we will use our Vellum Hair Constant to give this line some hair-like properties. So this is the basics of hair configuration or hair simulation as well in Vellum. So I'll create a Vellum Hair Configure. Okay, and this is what I'm getting. I've got a configuration. Basically the constant type here already is hair, and we can change the group type to points, and this will just ask the constant to apply on the points of the geometry. And then we have some mass here, we have some thickness. Okay, we can visualize all of them, and then if we come down, we have two of our important sections, which is the stretch section and the other one is the bend section. So the stretch section and the bend section in this Vellum Hair configure, in this Vellum Hair Constant, behaves exactly like our cloth. Okay, so the stretch stiffness, the stretch section here controls how stretchy the hair is, and the bend section controls how bendable or how foldable the geometry is going to be. Okay, so the stretch section, the stretch stiffness is pretty high, 1e plus 10, because hair is not very stretchy. It doesn't stretch like elastic. Okay, it just breaks off, and so we have stretch stiffness very high, and we have bend here, which is which controls the bendability or foldability of this object, of this hair. So we have the stiffness here, which is quite low, which is 0.001, and this is because we already know that hair are quite bendy. We can bend them however we like. Okay, so we can fold them however we like. So these are the things that, these are the properties that we are applying with the help of our Vellum Hair Constant. So after this, what I'm going to do is I'll just create a Vellum solver. Okay, I create a Vellum solver. I think I'll move this line up a bit, and I think I can increase the points here to 35, so we have enough geometry. And I'll come to Vellum solver. I'll just turn on the ground position here, so it will provide us with a collider, a ground collider. Now if I play this, let's see what we're gonna get, and you will see the hair just collides with the ground, and it bends after a point and it falls down. Okay, so this is basically it's behaving like a hair. If I decrease the number of points here, if I change the number of points to be 5, this is how it is going to behave. Okay, so whether a line is going to behave like a hair also depends on how many points are going to be there, because geometry matters in Vellum, as I have already said in the previous constants. So if I increase the points to 50, we will have a lot of points, enough points for this geometry or this line to behave like hair. So yeah, this is what we are getting. So here basically all these points define the bendability, or how foldable, or what is the bend angle, maximum bend angle that we are allowing these points. Okay, so what is the maximum rotational angle for these points? That's what we are basically dividing in simple language with the help of our bend here. So if the bend stiffness is very high, it will not be bending at all. So this is, I think, a pretty good example. Okay, and if I create a grid, this is a grid, and let me just decrease the size here to 2 by 2. Okay, and if I scatter some points here, and if I copy this line on these points, so I'll use a copy to point node. Copy to point, what this node will do is it will help us copy the geometry, which is our line, on these points that we have created here. So this is what we are going to get. These are the scattered points, and on these points we are copying our line here. Okay, just make sure that we have normal here. Okay, and when you have normal, you need to position this line in the z direction. This is one of the rules when you're copying anything on the points. So we have normals here. So first we had a grid, okay, and this grid we have provided some point normals to this grid, okay, and these point normals will be attributed or transferred to the scattered points that we have created here. Okay, these are the points which are getting scattered on this grid, and these points will also inherit, or they will also inherit the normals that we have created here. Okay, so if you want to visualize the normals on this points, this is what is a normal. And one of the rules is, this is one of the basic rules, you just need to follow this, that whenever you are trying to copy an object on a point, if you want the object to follow the normal direction, just keep that object in the z direction. That object needs to be facing the z direction. Okay, this is one of the rules in Houdini that you need to follow, and we are getting these. So if I just connect it to a Vellum hair, all these lines will get Vellum Hair Constraint or Vellum Hair Configuration, and if I play the simulation, let's see what we are gonna get, and all of them are behaving all of them are behaving like hair. So they do, for some reason, they do jump back when they fall down. They move like this and then they fall down after some time, but that's normal, that's okay. So this is one of the examples. And what if I want to remove the ground position, and what I will do is I'll just give some kind of pinpoints to all these hair. Okay, so let's say that all the hair should have some kind of pinpoint. So let me just create a line here. Okay, and I'll just create a group. This group is point, so I'll just name it to point. The group type is going to be point, and I'll select just one point, and I think the topmost point here is the 49 point. I think that is okay. Okay, so this is the line, and we have created a group for this line, and in that group, this point, the topmost point, is present in this group. Okay, wait, actually I think I changed the name of this group. Okay, so this group is called pin, and the topmost point is present there. So when we are copying this line on all these points, all the lines that get copied on the points here will have that group. Okay, so if you come here and if you come to the point group section, you will see that we have a group called point, and it has 1000 points. Okay, and that is because we have scattered 1000 points, and 1000 lines are being copied on each of these point has a line that is being copied on it. So we have a group here which has a point collection which is 1000 in number. Okay, now if I come to Vellum Hair, and maybe we can come to the pin to animation and use the spin group here. Okay, and if I run the simulation now, and let's come inside of our Vellum solver and create a pop force, and let's give some amplitude in the pop force. Now if I run this, let's see, and you will see that all these hair thing or all these objects are hanging because their topmost point are pinned to their original position. They are pinned, and the rest of the geometry is getting simulated, but the topmost point is pinned, and this is what we are getting basically. So maybe I can increase the number of scattered points here to 5000. Let's see. Wow, so this is what we are getting. All the top points are obviously pinned, and the rest of the geometry is getting simulated as hair. So we got a hair collection here, I think. And if I create if I want, I can create a collider here. So let's create a collider. I'll create a tube. Okay, so this is the tube. I'll just use this, template this, actually template this, and this is our tube. Okay, I want this tube to rotate in the x-axis, so I'll just come here, rotate it by 90 degrees. Let's decrease the radius scale here. We do not want it to be very thick. Let's increase the height and increase the number of rows and columns here, so that we have a high quality tube here, and also close the ends here. Okay, so now we have a collider, and we can obviously, what we can do is we can animate it. Okay, so on first frame, what I'm gonna do is I'll keep this tube here, and so I'll just give it some keyframes here, and on frame 72 I'll just move it ahead in the negative x direction, something like this. Give it a keyframe here, and now if I play this, now that we have connected our collider here, let's see what we are gonna get. And as expected, this is what we are getting. We have hair here, and they are hanging because the topmost point is pinned, and they are behaving like hair. Then suddenly we have a collider which is colliding them. And you know what we can do? If I give some color to this line, Yeah, if I give some color to this line, then we can give color to all of them. So let's come to this line. This line has 50 points, as you can see. What I'm gonna do is I'll use a resample. Okay, so what resample basically does is, if you have a curve or if you have a line, we can resample it. We can basically recreate it in a way. Okay, recreate it with a new amount of points. How many points do you want? Or we can also give some attributes here. So this is a resample, and what I want is I want to give it 50 points. So I'll just turn off the maximum segment length, and I'll just turn on the maximum segments here and create 50. And the reason we are using resample here is because I want to create a curve view attribute. Okay, so basically what the curve view attribute is doing is, from point 0 to point 50, it is giving a curve view attribute which has a value which is going from 0 to 1. Okay, so the first point here in this curve, or in this line, is this point, the point 0, and the last point is this point, the point 50. And we are creating a attribute here which is going from 0 to 1, 0 to 52, and the value of that attribute is going from 0 to 1. Okay, so basically a curve attribute gives a 0 to 1 value to this curve from its origin to till its end. Okay, so we have a curve view attribute which is going from 0 to 1, and with the help of this curve view attribute we can color this line. So I'll just use a color node and come to the color type. We are going to create a ramp from attribute, and I'll use curve view attribute here. And now if I show you, you will see that we have our line which is colored, and the value is going from 0 to 1. The color value is going from 0 to 1 because it is based on the curve view attribute. Okay, if I change it to white border, something like this, you will see the 0 curve view attribute value has a dark blue color, and the color is increasing to white because it is going from 0 to 1. Okay, the curve view attribute, because it is based on curve view attribute. So I can also change color here if you want, and instead of white, we can create a green. And the best thing I think we can do here is just come to the white border, change it here, something like this. Maybe we can change the color here, something like this. Let's make it darker green. Okay, so now we have a line which has a color something like this based on the curve view attribute. And if I visualize all the lines, this is what we are getting. Okay, and if I play the simulation now, I think we can change the color here. Okay, so now if I visualize this, so we have curves here which are behaving like hair because of our Vellum hair configuration, and then we have our tube which is behaving like a collider. Okay, and this is the kind of comedy show that we are getting here. As you can see, if we increase the amount of substeps here, this will behave even more nicely, because you will see that some of the hairs are getting stuck here in our collider. So we can increase the amount of substeps here, but it will take a lot of time. So what I'm gonna do is I'll decrease the scatter points here. So let's keep the amount of points to something like 1000 so that we can visualize this properly. Okay, and we have also increased the number of sub-steps here to 4, which means on every frame the solver is going to calculate 4 times. And now you will see that the hair are not very jumpy. They're not, they actually are behaving like hair now. See, they are not very stretchy. And if I run this, this is what we're gonna get. Okay, so this is the basics. These are the basics of our Vellum hair configuration. And what you can do is you can provide some geometry here to these hairlines or these curves if you want, if you do not want them to stay as hair, or if you do not want them to render as hair, you want them to give some geometry. What we can do is we can use a node called sweep node. Okay, so I'll just create an attribute delete, and I'll just delete most of the attributes, almost all the attributes for this thing. I'll keep p scale, and I'll keep the color. I'll also keep the velocity, and I'll just turn on delete not selected. So everything except this things, everything, all the attributes except these 3 are getting deleted. And after that, what I'm going to do is I'll use a sweep node. Okay, so what this sweep node does is it provides geometry to our curves. Okay, and we can decide what kind of geometry we want to give. So if we come to the surface shape, I'll create a round tube. Yeah, so just delete all the attributes except curve view. So instead of creating our colors here, what we can do is we can just take this, and I'll create my color here. So I've deleted everything except our curve view. So this is the thing that I'm getting. And in our sweep, the sweep is used to give some geometry to our curves or hair. And I've used a surface shape called round tube. Surface type is quadrilaterals, and I have kept a radius which is quite low. Okay, and you will see that the ends of this geometries are actually open. So what I can do is I can create end caps here, grid, something like this, and this is what I'm getting. Okay, and if I turn on the apply scale along curve, so what I can do is along this curve I can give it different scales. Okay, and if I multiply this with the radius, if I increase the radius, you will see the shape that I'm getting. Okay, and I can also change the type here to B-spline if I want. So this is what I'm getting. So we can create shapes like this. Okay, we can apply some scale along the curves. And this is some funny stuff that I'm getting. Okay, so this is the basics of our Vellum hair configuration. Now let's look at the 2 examples that I have created. Okay, so example 1 is not very different. Okay, if I play this, you will see that I've used the same methods that I've taught you earlier for Vellum hair configuration. So I'll just go through these. So basically what I've done here is I've used a sphere here. This is our sphere. Okay, I have given some normals to this sphere. Okay, normal points. You can add normals to points or vertices, whatever you like. I have scattered some points here. So the number of points that I have scattered on this sphere is 2000. Okay, and they are inheriting the normals here. And after that, what I've done is I've used the attribute adjust float node to give some p scale to all these scattered points. Okay, so all the points here which are scattered, they all have a p scale value. Okay, so when we are copying something on them, the thing which is getting copied on these points will inherit that p scale, so they will know what the size should be of that copied thing. Okay, now we have a line. As I told you, this line has 10 points. I have resampled it, and basically we have 10 points here. And I've used a group expression node, so you can create any kind of group, but I have created a group expression node, and in this I have used a default method, which is the first pointer parameter. So what this will do is, when you have selected the group type to be points and you have named the group whatever you want, this group expression will just select the first point in this geometry. And what is the first point in this geometry? This point, which is a 0 point. Okay, this 0 point is the first point in this geometry, and it is present in this group. Okay, so now when we copy this line on all these points in the sphere, we will have a pin group included in this lines. Okay, so when I'm copying all these lines on these points which are inheriting the p scale value, which already have a p scale value that we have given to them, the p scale, which is going from 0.63 to 1.034 and some element size here. So all these lines are inheriting a p scale value, and they also inherit the pen group. Okay, so basically all the points which are here, all these points, the first point of all these lines, which are somewhere here in the root, they will be pinned. Okay, they will not move. And then what I've done is I have applied some Vellum Hair configuration here. Okay, simple Vellum Hair configuration. I have not changed anything. The only thing that I've done here is I have used the pin to animation, and I've pinned the root points here. Okay, that we have created here, and then inherited by all these points or all these lines. So we have pinned the group, which is called pin. I have attached it to our Vellum solver. Okay, and in the Vellum solver I have just used a pop force here with some amplitude, and there's no gravity here. Okay, so now when I'm playing this, I am getting this random movement of all these hairs or these curves, which is looking quite relaxing. If I increase the scattered points here, you will be able to see them even more nicely. Okay, so if I play now, it will be better if I just keep it at 2000. It was better to visualize that way. So this is the moment that we are getting, and I'll just tell you that after the line I've used a resample, and when I use the resample node, I have just turned on the curve view attributes so that we can color this later. So after the Vellum solver, what I've done is I've used the attribute delete, and I've deleted everything except the curve view attribute here. Okay, and I've used a resample again. Okay, so to give this hair good resolution whenever we are rendering, it will help us. And after that, I've used a color node here, and I've given a color value to these lines with the help of the attribute curve view. Okay, which is going from 0 to 1. After that, I've used the sweep node here, as I've showed you earlier. Surface type is round tube, and quadrilaterals, radius value, and apply scale along curve. You can play with those values. And this is something that I'm gonna get, some kind of aquatic sea plant type thing. And it's looking all right. So this was the first example. Now we can move on to our second example. Okay, so the second example is here, and it's pretty basic. We have two kind of vellum constants here working. One is the vellum hair here, okay, and the other one is the vellum balloon configuration, which is this one, and both of them are getting combined here. So let's see how I did this. The first thing that I did obviously was I created a grid here. I'll just arrange it properly. So this is a grid, okay, this is our grid, and what I've done here is I've used a normal here, normal node here to give some normal point, here to the points to our geometry, okay. And after that, what I've done is I have scattered some points here, and with the help of our scatter node, and I have decreased the relax iteration. That's why our points are looking like that. If I do it the default value, which is 10, then we will get proper distance between these points, but I've kept the relax iteration to 1, so that we have some randomizing of the points here. After that, I have used a attribute adjust float node, which is basically the node which gives us our p scale value, and every single point here has a p scale value now, and which will be inherited by the line, okay, when we copy them to our points. So the values are going from 0.268 to 0.191, and I have given an element size of 0.587. So now I have a line here that I've used, okay, this is our line, and in the z direction obviously I have resampled it, and I have given it some I have given it 10 points here with the help of our resample. I've used or turned on our curve view attribute. I've used a group expression like before, okay. So it is in this group we have this 0th point, okay, the point which is at the base, which is at the root of this geometry. What I've used here is a bend node, and with the help of our bend node I'm bending this line or curve here, and then I have used a color node, and with the help of our curve view attribute I have provided color to this line, and I have copied this line to all our points here. So this is what we are getting basically, okay. What I've done after that is I've used a Vellum hair configuration, okay, and with the help of this Vellum hair configuration or Vellum hair constraint, what we can do is we can provide these lines or curves with hair properties, okay. So we will provide them with the stretch properties and the bend properties of hair, and I have used the pin group that we have created earlier to pin the points which are the root points here, okay. So all those points which are at the bottom here will be pinned, okay. They will not move from their position, they will not take participation in the simulation. Everything else will take participation in the simulation. Now, as I have teased you earlier, I have used a Vellum pack node here, okay, and this Vellum pack node will help us in combining this Vellum hair with the other Vellum objects, okay. So the other Vellum objects that I've used here is this. I'll just template these here, and then I've created 3 spheres here of the size 0.5 uniform scale, okay. So these 3 spheres are then being merged. I have provided them with colors. I've used a group called which is a point type group, and I have called it sphere. After that, I have used a Vellum balloon configuration here. I just created a Vellum balloon configuration, and this will provide you with the Vellum cloth constraint and the pressure constant. And here you can see the values that I've used. I have not changed much. These are default values. The pressure here is 1 plus 10, which is the highest, and I have applied both of these constant only to this specific group, which is the sphere, okay. Then I have used a Vellum pack again here, and after the Vellum pack we have the geometries here, pack geometries. I have combined them all with the help of a merge, I have used a Vellum unpack node here, and then I have connected these with our Vellum solver. Okay, so you can see both the Vellum objects, in fact all the Vellum objects, the hairs and our spheres here, or balloons here, they are combined and they are collectively connected with our Vellum solver. Okay, in the Vellum solver I have created a ground position here, ground plane, and everything else is okay. The only thing that I've done here is, if you come inside our Vellum solver, I've used some pop force and pop vents here. So the pop force, the first pop force that I've used for our hair. Okay, so what I've done here is I've used the group sphere, and in sphere we only have these 3 spheres, but this sign basically says apply this forces or everything that is here on everything except the sphere. Okay, so these amplitude and the swirl size and everything that I've used here will be applied only on our hair. Okay, the other thing that I've done is I've used a pop vent here, and this pop vent will be only applied to our spheres. So it is basically given in the positive z direction. So these hair will have a pop force which is applied to them, and then we have this balloon spheres which have applied on them the velocity, pop vent, and we are providing them with the velocity of 1 value in the positive z direction, so they will move somewhere here. And after that I have used I've also given the gravity to these spheres, because without gravity they will just move in the air. So I have provided these spheres with some gravity, minus 9.8 force in the negative y direction. I have applied 9.8 force. Okay, and everything else is okay. So after I have connected all of these, when I have run this simulation, I have connected a Vellum post process and I have not done anything here, and then I have cached it. So this is the result that we are getting. We have combined our balloons here, okay, which are getting affected with the help of our gravity, the pop force that we used, and our pop vent, and they are interacting with our hair, and the hair are already getting affected with the pop force that we have applied on them. Okay, so this is the result that we are getting. This is what we are getting, and this was the second example. So I hope you understand both the examples here, and if you have any questions you can always ask me. But this was the second example in our Vellum hair configuration. Okay, so now we have another constant which is very interesting, and this is attached to geometry. So what if you have a Vellum simulation or a Vellum object and you want it to get attached or stick to a collider? Okay, so in this example you will see that we have a cloth object here, okay, and this is attached to this object which is a collider, which is behaving as a collider. So what can we do to do something like this? First I'll run this, and so that you can see properly what is happening here. We'll see we have this test geometry and we have attached or stick cloth object to it. So this is what we are going to learn in this video, in this one. So the constraint that we are going to use is attached to geometry constraint. I'll just show you what the basics are first, then we will come to this example. Let me just create a geometry network first. I'll call it sim. Okay, you can change the color if you want. I always do. And let me create a very basic example. So let's create a box. So we have a box here. All right. Let me move it properly. I'll just rotate it in the x direction. Rotate it in the x direction. Something like this. And what I want is I want this to behave as a collider. Okay. So maybe this is a geometry that I have animated, something like this. Let me create a transform node, and let's say that I have animated it up and down. Okay, I've got maybe I've got a character animation, or maybe I've got a got some kind of geometry, animated geometry that I have received from someone, or maybe I have created it. And for example, let me create a sine function for this so that it will move up and down. Okay, so if as multiplied by 10, so let's say that we have a geometry. Oh, sorry about that, not rotation. We want this geometry to move in the y direction, something like this. Okay, so let's say that we have a geometry like this, animated geometry, and we want this geometry to behave a certain way, like, sorry, so let me start by creating a geometry network. I'll call it sim. You can change the color if you want. We'll go inside and let me create just a basic, pretty simple example here. So I'll create a box here. Okay, and this box is pretty basic. I'll rotate it in the positive x axis, something like this. And then what I'm gonna do is I'll give it some animation. Okay, in the positive y axis and negative y axis. So we want it to behave. We want it to move up and down. Okay, something like this. So let's say that you have got a geometry from somewhere else, or you have created a geometry. Maybe you have a character animation, and you want to attach some kind of vellum object to this. So what I'm gonna do here is, this is our box and this is our main geometry, and I want to attach a cloth here. Okay, and while this geometry is going to be behave like a collider, I want that cloth object to obviously simulate like a cloth. So what we can do is, this is going to behave like a collider. Okay, this is our main geometry. I'll create a null, and this is the geometry where we want to attach our vellum simulation, any kind of vellum simulation. Maybe it can be a cloth or a balloon or anything else. We want our vellum simulation to attach to this. So in this example, what I'm going to do is, I'll create a grid and I'll attach a grid or a cloth here to this geometry. Okay, I'll template this and let's see this grid. The size is too big, so I'll just decrease the size to 1 by 1. I'll rotate it in the x by 90. I'll move it down somewhere close to our box here. Okay, and I think I can move it here. Yeah, so this is our grid. Let me just visualize smooth wire shaded. Okay, so this is our grid, and I'll just decrease the rows and columns to 2 by 2. And I'll create a remesh node so that we can remesh it properly and have enough and high quality triangulated geometry. Decrease the target size to 0.1, or actually 0.05. Okay, now if I template this, you will see that this is our original animated geometry which we want to behave like a collider, and this is our cloth. We want this to simulate, and we want to attach both of them. Okay, and for that, what I'm gonna do is, I'll use Vellum Attach to geometry constraint. But first, let's give this cloth the Vellum Cloth Constraint so that it has cloth properties. So this is our Vellum Cloth Constraint. We have given Vellum Cloth Constraint here to this grid here. Okay, change the group type to points, and we do not want any changes here. Okay, the default setting is fine for this Vellum Cloth. Other than that, what I'm going to create is Vellum Attach to geometry, this constraint. Okay, and what this constant will do is it will help us in attaching our collider geometry to our Vellum object. So I'll just use this collider and connect it in the collider section here, in the collider input. Okay, and when we come to our attached geometry, you will see that all the points in our Vellum cloth are getting attached to the closest point in our collider. Okay, and this is okay, but we do not want this. We do not want all the points of this Vellum cloth to attach to this collider. We only want the closest point here, the closest point of the cloth to get attached to the primitive or the closest points or the closest part of the collider geometry. So I'll come to the Vellum Attach, and one thing that I'll turn on is max distance. Okay, and with the help of this max distance, I can control by what distance all the points can connect to our collider geometry. So if I increase it slowly, you will see first the points which are closer to this collider geometry will get connected to the, will attach to the collider geometry. But if I keep increasing, you will see more points are getting attached to the collider. Okay, and we can control it here. You have to turn on the maximum distance here, but as I said, we only want the closest points to attach to our collider geometry. So I'll just keep it somewhere here, something like this. Now if I use a Vellum solver and if I attach it here, so keep in mind the one mistake that we have done here is we positioned this grid, we positioned this collider, and this is our template. So I positioned the grid according to the frame 10, and it was functioning pretty nice, but the solver is going to start from frame 1. So I need to position my grid here according to the geometry from frame 1. If it is in the middle, as you can see, it's going to create some problems. If I run this, this is what I'm getting. Okay, it's attached to somewhere in the middle, which we do not want. So position it properly on frame 1 itself. Okay, whatever Vellum object you want to attach to your collider, position it properly on frame 1 so that you don't face any problems later. So I'll just move it down, something like this. So I position it properly according to my frame 1. And now if I go to our attach geometry, you will see this. I can even decrease the maximum distance. And now if I run this, you will see, and if I give some pop force so that our Vellum object is flowing, so now you will see that our Vellum cloth object is attached to our sphere here, our box here. Okay, and I can obviously use our Vellum post process. So this is what we are gonna get. The collider geometry is not gonna come out of our Vellum solver. Okay, so you'll have to use a merge node later, something like this. Okay, I'll have to provide some normals here for this sphere. So this is what we are getting. We had a cube and we wanted to attach a Vellum cloth object, simulated cloth object to this. So we have used a Vellum attached geometry constant. Okay. Okay, so this is working pretty fine. Now we can move on to our main example here. I'll just close this and I'll turn this on. So if you look at this, this is working similarly. I have used the same principles that I've used in the same example here that I've shown you. So there's nothing extraordinary. We have basically we have a test geometry which is moving like this. Okay, this is our test geometry, and we have given some kind of animation to it. It is moving something like this. And to do that, what I've done here is I'll give you a brief overview of this setup. I've used a curve, Bezier curve, and then to this Bezier curve, what I did was I created this Bezier curve. I gave it some proper form. I've used a resample node here, okay, so that we have enough geometry for this curve. After that, I've used an orient along curve so that our curve here have proper normals. Okay. After that, I use a carve node, and what this carve node does is basically we can control the beginning and end of this curve. Okay, so first U is basically this end, and the second U is basically this end. So first U is, I have kept it at 0 position, okay, which is its original value, and I have animated the second U, so that's why it's growing like this. So this second U is going from 0 to 1. Okay, and after the curve, what I've done is I've used a group range, and this group range I have named the group point, and the group type is points, and I have used the range type 0 to 1, and I have inverted it so that we are only selecting the last point. In this group called point, we are only selecting the last point here, whatever the last point is. So if you come in the beginning, we have a point here, and when we move this, the last point here is going to be kept in this group. Okay, after that, what I have done is I've used the test geometry, this test geometry, and I have copied this test geometry only to the target point, which was a group point. Okay, and as you know that this group is only keeping the last point in this curve, so that's why this test geometry is now present at that position of the point, and this is the moment that we are getting. It's a pretty basic setup. You can create it very easily. So this is our geometry, and after that, what I've done is on frame 1, I have created a grid here. Okay, so this is our grid. I'll just template our test geometry. This is our grid, and what I wanted was I wanted this end of this grid to get attached to our test geometry. Okay, so I've used a group. I only wanted this points here to get attached to this group, so I created a group, and in this group I called it the snap. The group type is points, and I selected all these points, only these points, because I wanted only these points to attach to our test geometry. After that, what I've done is I've used a ray node, and what a ray node basically does is it's going to take the group that we have selected here. It's going to only apply to this group, snap group that I've created, and we are taking another geometry, which is our test geometry, this geometry. What basically we are asking to this to this ray node is take the groups that we have take the points that we have selected and position them, change the position of those points to the nearest position on this geometry. Okay, so what basically we are saying is, look at these points. Okay, what is the closest position for these points on this geometry, and then move them there. So I've used the ray node and I've used the minimum distance method, and that's why these points are positioned on the closest distance here of this geometry. After that, what I've done is I have remeshed this our cloth, I have given a Vellum Cloth Constraint here to this grid here, and after that I have used a Vellum Attach to geometry. Okay, similarly to the previous example, and here I have just used points. Group type needs to be points, and I have turned on the maximum distance and I kept the maximum distance to 0.01. If I increase it, a lot of things are going to get attached, and I do not want that. So 0.01 was perfect, and I've not changed anything here. The Vellum Cloth setup is also default, so there's no change there as well. And after that, what I've done is I've just used the Vellum solver. When nothing else is here, no forces are applied. This cloth is getting attached to this collider geometry of a animated object here, and I've used a Vellum post process, and this is basically what I'm getting after the simulation. As you can see, the cloth is flowing. The initial points, the first points, are attached to our collider geometry, and this is behaving now like a Superman cape. I've colored it red, and this is our final simulation. Okay, so the Vellum attached to geometry is very powerful, and it's not very difficult to use. You can do a lot of things with it, and now we will see the next example. Okay, so in this example, what we are going to cover is this, probably one of the most popular effects in Houdini Vellum Cloth, which is the cloth tearing effect, or as we technically call it in Houdini, the weld points constraints. Okay, so this is what we are basically doing here. We have a cloth here, and then with the help of a collider, we are breaking these cloth. Okay, and then in the second example, we have a statue. We have an object here, the 3D this geometry that we have here, and just imagine that it's wearing some kind of clothing over it, and then that clothing is getting torn off with the help of a wind effect or something like that. Okay, so how do we do that? The basic principle I'll tell you here, okay, before I give you a simple example. So what we do basically when we are doing this is we have an object, and this object can be anything, like it can be a cloth, and it can be any other 3D object like this also. So we have an object which is a cloth, and then what we do is we fracture this object. Okay, fracture this object. So by fracturing, what I mean is we do multiple fractures here. We divide this geometry. Suppose this is a cloth geometry, this is our grid. We divide this grid into multiple objects by fracturing it. Okay, so we fracture it with the help of Voronoi fracture or some kind of other fracture, and we do multiple fractures of this. We separate it multiple times. Okay, we create a lot of parts of it, and after that, after fracturing this object, we reconnect or connect this object. Okay, or better word is reattach, I think. Reattach this object, or another word if you want is stitch. We stitch this object back again with the help of weld constraints. Okay, so the first thing that we do is we have an object. We divide that object into multiple parts with the help of fracture nodes, and then we fracture this object, and after that we reconnect this, rebuild this, or reattach or restitch the divided object into one object with the help of our weld constraints. Okay, and then in simulation we manipulate the properties of this weld constraint. Okay, so the weld constraint basically stitch them together again, they reattach it or rebuild it, and this weld constraint can be manipulated because it has some properties, and we can manipulate those properties, and we can decide what part or which parts of this object can stay attached, or which parts of this object can will need to, you know, just tear apart from this main object. So basically this is the point. We have an object, we fracture that object with the help of our fracture nodes, then we rebuild it, reconnect it, or stitch it together again with our weld constraint, okay, Vellum Weld Constraint, and then in our simulation we can manipulate these weld constraint, and we can decide whether the object stays attached or we can break it apart again in simulation. Okay, so this is what we are going to do basically. Okay, so we'll start with a simple example. I'll just create a geometry network. I'll call it sim. Can change the color as well if you want. And let me create a grid here. Okay, so this is our grid. I'll change the size here to 2 by 2, and I'll also change the rows and columns to 2 by 2. So we have a grid with 4 points here. I'll use a remesh node like always to give a high resolution triangulated geometry. 0.05 target size will be enough. Okay, so as I said, the formula is that we have our geometry. So let's take this grid, and we want this to behave like cloth. Okay, and if we want this to tear up, first what we will do is break it into multiple pieces before using our constraint. So we have our grid, we will break it into multiple pieces. So I'll use a fracture, and the type of fracture that I'm going to use is edge fracture. So what this edge fracture will do is it will create multiple edges here, and with the help of those edges it will break it into may break this object into multiple pieces. I'll use this edge fracture, and I've already used the edge fracture, but we cannot visualize the breaks here. So to visualize the breaks, turn on the primitive pace, and you have to turn on the piece attribute as well to visualize this. So now you can see that this object has been divided into multiple geometries, something like this. Okay, so you can control how many pieces you want by here. Okay, the more amount you give, there will be more pieces. So I'll just keep it at 10. Okay, so this is our geometry now. I'll just stop visualizing this, and I can also show you that this has been divided into multiple pieces with the help of an exploded view. So now you can see this was our original geometry, and we have divided into multiple pieces or break it into multiple pieces. Okay, so this is that. This is a very good node to visualize a divided geometry. Okay, so this is our edge. Now what we can do is we will use a Vellum Cloth Constraint. Okay, and this obviously gives our object cloth-like properties, and now we will connect it with our Vellum solver, which is the brain for our cloth simulation. Okay, and now what I'm going to do is I'll just paste a sphere here. I'll use a sphere here as a collider. I'll move it down something like this, and in the Vellum solver I'll turn on the ground position, keep it here, and now if I run this, you will see that our cloth is behaving like cloth, but it is already broken into multiple pieces. Okay, if I rotate it in the Z direction, something like this, And if I play this now, yeah, see, this was our cloth. This was our cloth geometry that we wanted to behave as cloth. This is our grid. We broke this grid into multiple pieces, okay, with the help of our edge fracture. These are the pieces. Then we used our vellum cloth on this. So all these pieces are getting vellum cloth properties with the help of this vellum cloth constraint. Okay, so they have got this stretch properties and the bend properties, and all the cloth pieces have those. When we run the simulation, they fall down and they break apart instantly. They are already broken apart because we have not reattached them. Okay, so if I rotate it even further, something like this, and if I move this in the up direction, now if I run this, you will see that this was already broken. It's not like we have reattached it with the help of our vellum cloth. The separated or divided pieces is given the cloth-like properties, and they are divided on the first frame itself. They are not attached, or they are not sticking with each other. Okay, this is what we are getting: separated parts of the cloth behaving like cloth. Okay, now what if we want to reattach them? Okay, so for that we have a node called Vellum Weld Points. Okay, keep in mind this is the Vellum Weld Points. This is what we are going to use. If you want to actually, I just wanted to make sure that you know this also. I'll use another Vellum constraint, and these two constraints are actually quite similar. Okay, so I'll just give you the main crust of this. If you have one geometry, okay, so we had this one geometry, which is this grid, then we break it into multiple pieces. Okay, but this is one geometry only. We break this one geometry into multiple pieces, and these are the pieces. If you want to reattach those pieces, if you want to rejoin those pieces, you will be using weld points. Okay, the constant type needs to be weld points. Okay, if I use this Vellum weld points, then I'll be able to reattach the divided geometry. It was one geometry, then we used our edge fracture to divide it into multiple parts, and if you want to reattach it, you will use weld points. Okay, and there's another constant which is called the stitch point constraint. What this stitch point constraint does is it helps us to connect or join two different objects. Like if I had a grid here, if I had this grid, let me just make it 2 by 2. So this is one grid, and if I have another grid here, I'll just merge them so that you can see them both. These are the two grids, grid 1 and grid 2, but they are very close to each other. And what if we want to join them together? Then we will use Vellum stitch points. Okay, if you want to join two different Vellum objects, you will use Vellum stitch points. And if you want to join, or if you want to reattach or stitch or merge the objects which have been divided, they were part of one object and then they were divided, and you want to rejoin them or reattach them, then you will use the weld points here. Okay, I'll just write it here, even though we will be looking at an example of stitch points later, but I just want to make sure. Weld points constraint is to attach or join the multiple pieces of same object. Okay, and stitch points same. Sorry. Okay, weld points is constraint is to attach or join the multiple pieces of same vellum object, and stitch points is to attach or join two different vellum objects. Okay, so we had one geometry, we divided into multiple parts. To reattach them, we will use vellum weld points. Okay, if we have two different kind of geometry or three different kinds of geometry, let's add a sphere here as well. This is a sphere. There are two grids and one sphere, and if you want to join them together, if you want to attach them together, then you will be using vellum stitch. Okay, so we are looking at an example of weld points. We have one geometry which is divided and we want to rejoin it or reattach all these divided parts. So we will use vellum weld point. Okay, the weld points constraint, and I'll make it the group type. I'll change the group type to points, target points also points. And if I look at it here, you will see that this vellum weld points is obviously showing you the connected edges. Okay, so this is our geometry. If I separate it a bit, these are our broken geometries, and with the help of vellum weld points, we have attached them together back. Okay, so I hope you understand the concept here. If you have one vellum object and if you have divided it into multiple parts and you want to rejoin it, you will be using vellum weld points. Okay, now if I play this, we have our geometry here. It was broken into multiple pieces, and with the help of vellum weld points, we have reattached those points. Let's see if this behave as one combined geometry or not. And it is behaving like a one combined geometry, as you can see. This is behaving like one object now. All right, and that's what we wanted. Now, what if we want to break it again, but within the simulation? Okay, we do not want it to stay separated from the beginning, but during the simulation, at some point of time and at some frame, we want it to break. What can we do? We can use our breaking area here and use the breaking threshold. Okay, so with the help of the breaking threshold, we can decide one of the things. If the stretch stress is higher than this threshold, okay, then it will break. Or we can also bend stress. Okay, if the bending is too much, then it will break. Or if stretch distance, if you are pulling it too much, if there's too much distance, if it is too much pressure for the stretch distance, then it will break. Okay, so there are multiple things here. I'll keep the stretch stress, and if I play this again, you will see they are breaking. Once the threshold of stretch stress has reached this point, it will break. The connection will break. Okay, something like this. So breaking threshold has multiple types here: stretch stress, bend stress, stretch distance, or stretch ratio. I always used to prefer stretch stress. Okay, and if the threshold here is bigger than 0.033, then it will break. And this is what we are getting. So this was the first common example here, and now we can look at our main examples. So what I've done here is, if I first look at this, you will see that we have a test geometry here, and this test geometry has a layer above it which is a cloth layer, but because of too much wind or some kind of forces, it is breaking away. Okay, so I've used the same method here. So this is our test geometry. After that, what I've done is, this was our test geometry, but I did not want these objects here, so I have used a blast node and I've deleted all of them. After that, I have given a point normal to this geometry. Okay, I've used a peak node, and what peak node does is it moves the object or the face in towards the direction of the normal, and I moved the geometry, or moved all the faces, all the edges and all the points here by 0.002 meters towards their normals. Okay, basically that's what I have done. And then I've used attribute delete to delete the shop material path, which was the shader that we had here. Okay, so I've used the attribute delete node to delete that, and I've used a triangulate node to give our geometry some triangulated shapes here. Okay, so we have triangulated faces, and after that I've used a edge fracture, just like in the previous example, and this is what we're getting. So with the help of the edge fracture, I have broken it into multiple pieces. I divided this geometry into multiple pieces, and I want it to behave like cloth, obviously. So I've used a Vellum Cloth Constraint. Okay, and then with the help of the Vellum Weld points, I have reconnected all those divided points here, as you can see. Okay, I've used the same method. We had a geometry. Basically, we have a geometry. I've used edge fracture to divide it. Okay, before our simulation. Then I have given this multiple geometries, this multiple broken geometries, the Vellum Cloth Constraint, so they will all behave like cloth. But I have also used a Vellum Weld points to reconnect them. Okay, and this is what we are getting now. And after that, I have used a Vellum solver. Okay, this is our Vellum solver, and this is our cloth geometry now. But I also wanted this 3D geometry to behave like a collider. So if you can see, the original geometry is this. This is our original geometry, and this is our original geometry, and this is our peak geometry. So with the help of our peak, I have moved our Vellum cloth geometry 0.002 meters in the direction of the normal, so they are not colliding with each other. Okay, so this Vellum cloth geometry will be sitting up, and the collider geometry will be sitting down. Okay, so they are not in contact with each other on the first frame. Okay, so that is what I have basically done. We had our geometry. I have used edge fracture to divide it into multiple parts, separate it into multiple parts. I used Vellum Cloth Constraint to make them behave like a cloth, give them cloth properties. Then I've used a Vellum Weld points to attach them together. I've used Vellum solver for our Vellum solution, and I've used the original geometry as our collider here. Okay, and inside here I have used a Vellum pop vent. Okay, and what this basically is doing is I have given a wind velocity, a variable wind velocity which is flowing in this direction, in the positive z direction, and in our vellum weld I have turned on the breaking threshold. So if the wind velocity is too high, some of the joints here will break. Okay, as the breaking threshold is not very high, it's a 0.1. So if the wind velocity is too much, the joints that we have created here with the help of our vellum stitch weld points, they will break and the clothes will flow away. Okay, so if I play this is what you will see. The joints which are breaking away, they are just breaking away and they are flowing in the wind. Okay, and the joints which are not going above the threshold for stretch stress, they are just staying together, attached. Okay, after this I've used a vellum post process, and in the vellum post process I have not done anything. I just turned on the apply welds, so the geometry is looking smoother. If I show you, smooth shaded, this is how it was looking. So there was some normal mismatch here, as this was joined with the help of our vellum weld points. They were held together. So I've used a vellum post process, and in the vellum post process I've turned on the apply welds so that normals are functioning properly and they are looking or behaving as one object now. So initially it will look like one object, but it obviously is made up of multiple objects. Okay, multiple cloth objects which are stitched together or welded together. Okay, so this is our color, and if you see it with our collider, this is what we are getting. So this was one of the examples, pretty basic example. And if you look at it, the other example here, so we have a cloth object, and with the help of this collider we are breaking it into two pieces. So if we look into this example, you will see that we had a grid here. Okay, I remeshed it, and after that what I did was I use a edge cusp. So the edge fracture is nice to give randomly some fractures to your geometry. Okay, so if I turn this on, if you want to give your geometry some random fractures, then edge fracture is pretty nice. But if you want a controlled method, then, and if you do not want to use if you do not want to create too many separate geometry, then the edge cusp is also nice. Okay, so what I've done is I've used the edge cusp, and then I have created a line here. I have selected the edges here. Okay, so I'll just show you. I'll create an edge cusp node. This edge cusp is then connected to our main geometry. Okay, and then what I've done is I've selected these edges here, and I've created this long edge here in the main edge cusp here. I have selected all these edges one by one. So I have created an edge path here, and with the help of this edge, what we are doing is we are dividing this geometry into two parts. Okay, so I have created this edge here in this edge cusp, and I am dividing this geometry into two parts here, this part and this part. And I've also turned on the cut boundary points. Okay, so if I use a exploded here, this is what we are getting. Okay, but if I turn off the cut boundary points and if I use the exploded, it will not be moving ahead because it's cut in the middle. it's not cut on the boundary on the edge here. So you need to turn on the cut boundary points also. If I use exploded, this is what we are getting. Okay, so with the help of this edge cusp, what I've done is I have divided this geometry into two parts, and now what I can do is I've created a group, and this group is created to single out all these points. Okay, all the edge points here. This group is created to group all these edge points here, all the points which are at the edge here, and these points will be used as pin points here. Okay, so what I've basically done is I've used a bounding type object, and I've used two boxes here, and I'm using two boxes to select all these points, and these points will be used as pin points here in our vellum cloth. So after selecting the pin, creating the group called point, I've used a Vellum Cloth Constraint to give this object cloth-like properties, cloth constraints. Okay, and here in the pin to animation, I've used the point group here. Okay, which is the pinpoint group. After that, I've used the same method. I've used the Vellum Weld points here to reconnect the broken geometry. Okay, so there was this edge here which was dividing this geometry into two parts, and with the help of this stitch, with the help of this weld points here, we have connected them back. Okay, and just keep in mind, because I wanted to break, I have turned on the breaking threshold here, and I've kept the breaking threshold here at 2. Okay, and in the Vellum solver, I have not done anything, I have not made any changes, but I am using a tube. This is the tube, and I have animated it here so that it is moving down, and I am using this tube as a collider. Okay, so with the help of this tube, I am breaking the threshold here of this vellum stitch. Okay, I hope you understand this. This is a vellum stitch. This is a vellum stitch, and I have given a threshold of 2. So if the breaking threshold of the stress is more than 2, this bond will break. Okay, this weld points will break. This welding will break. Okay, and to break that welding, to cross that threshold, I am using a tube here. Okay, as a collider. So this, if we run this, this is what we are going to get. Let me just reset the viewport. Okay, so if I run this now, this is what we're going to get. The collider will collide with our cloth, and it will break the threshold points of this joint here, this welded points here, this welded section, and it will break it into two pieces again. Okay, so I hope you understand that. The principle is the same, the working method is the same. We had a grid, this grid, then I used the edge cusp here to break it into two parts here. I used this edge to separate this object into two parts. Then I used a group here to select all these points which will be performing as pin points. I've used Vellum Cloth Constraint here to give cloth properties or cloth constraint to this object. I used the Vellum Weld points to reattach those separated joints here. Okay, and then when we are running the Vellum solver, I am using this colliding object as a breaker for this welded points. Okay, so if you run this, this is what we are getting. If I merge them together, you can see we have a cloth object Okay, it is looking as one object, and then we are using our collider to break it into two. We are tearing it apart. Okay, so this was the second example. I hope you understand it. If you have any questions, just let me know. We will move on to the next one. Okay, so this is the Vellum stitch points constraint. Okay, and what we do. Okay, so in this example, in this video, what we are going to talk about is the Vellum stitch points. So previously I talked about, or we did a couple of examples of how Vellum weld points work. So if you have one object and if you have divided it into multiple geometries and you want to reattach it or rejoin it and then break it, then you can use Vellum weld points. One object, divide it, and if you want to rejoin it, use weld. Okay, so you can weld it. But if you want to stitch together multiple different Vellum objects, then or different kinds, then you will be using Vellum stitch points, and this is what we are going to cover in this video. Okay, so here you can see that we have a rope like structure here. Okay, if I run this, and then attached with this is a cloth like structures here. Okay, so we have a Vellum hair constraint running alongside with our Vellum cloth constraint. So this is what we are gonna do. Okay, let's see this example here. So I have a line here. I have this line, and this line is going to behave like a rope. Okay, so I'm gonna run a Vellum hair simulation or hair configuration on this. This is a line, and what I'm gonna do is I'll select the 2 points here, the first point and the last point, and I'll keep these points as pinpoints. Okay, so I've used a line here, then I have used a group here, and I have in this group I kept all of them. All the whole line is in this group, so that after the simulation, if you want to separate them, if you want to split them, we can do this with the help of our groups. Okay, so we have a line. I have put this line into a group called line, and after that I have used a Vellum hair configuration. Okay, and in this Vellum hair configuration, I have not changed any kind of settings here. The stretch settings and the bend settings are all default. The one thing that I've done here is in the pin to animation section, if you come in pin points, I have selected the first point and the last point here, the 0th point and 30th point as pin points. Okay, so now if I run this simulation, if I use a Vellum solver here, I'll just show you. If I run a Vellum solver here, you will see this is what I'm gonna get. Okay, this curve or line that we had has hair-like properties, and because we have pinned those points, this is behaving somewhat like rope. Okay, and that's what I wanted. So this is the hair solution. But what I want was, I also wanted to attach some cloth-like structures here along with this hair. So what I'm gonna do here is I'll just Vellum pack this. Okay, so I'll pack this geometry and constraint, and I'll create another set of nodes here. Okay, and this will help us in creating the cloth like structures that I wanted. So I'll template this line here, and if we see that this is our line, and then I have created a grid here, but this grid is too big. We will need to scale it down later, but for now a grid of scale 10 by 10 and of rows 2 by 2 is here. After that, I have used a triangulate node. And just to visualize it properly, I'll just turn on the smooth wire shaded. So this is triangulated now. Okay, so we have two pieces here, and both the so this one geometry, which was a quadrilateral face, now it is a triangulated. Now we have two triangulated face here. Okay, if I delete one of the faces, we will have this, a triangle here. I'll transform it with respect to the scale of our rope here. Okay, so what I've done here is I've used a transform node. I have uniformly scaled it to 0.01. Okay, and then I have rotated it in accordance with our line here. Okay, what I've done here later is I've used a remesh node to give it proper geometry. I've used a group called cloth, and okay, so I've used a group called cloth here, and with the help of a bounding box, what I've done is I have selected the topmost points of this cloth like structure. Okay, so what I basically want is I wanted to select these points here, and I only want these points to attach to the hair here, this rope like structure. Okay, we do not want any other points to stitch or get attached to this. We only want these points, these top points of this cloth, to stick or to stitch with our line here. Okay, so that's why in the group called cloth I have selected all these points. After that, what I have done is I've used a copy and transform node, and I have created multiple 8 copies here. Okay, and I have kept them in a proper distance from each other. They are not in contact with each other, they are away from each other, and there are 8 copies. And in our group, because we had already created a group called cloth, and we have selected these points, because we are creating copy, we will be copying those groups as well. So if you come in the cloth group, we have 136 points. Okay, after that I am just running a basic Vellum cloth configuration here. Nothing different here. All the settings are default. So Vellum Cloth Constraint is here. I have used a Vellum pack node here to pack those geometries, and now I am merging both the pack geometries, the hair geometry and the cloth geometry, and we are merging them together. And now I am using a Vellum unpack node. Okay, now what I'm going to do is I am going to use a Vellum stitch point constraint so that we can stitch the cloth geometry and the hair geometry here. So let's use a Vellum stitch points here. Okay, this, and I have used one Vellum stitch points here, and if you come here, you can see that the constraint type is stitch points. In the geometry section, I've used the group called cloth. Okay, and in the target geometry, the target group is line. So basically what I'm saying is apply the Vellum stitch on all these points that we have selected of the cloth geometry. Okay, and the target, the geometry that you need to stitch with these points, is the line geometry. Okay, and the 2 important things that we need to keep in mind here is that you need to turn on the use closest location on primitive. Okay, so what these points on our cloth geometry is going to do, they are going to look at the target, look at the closest point or the closest distance. Okay, look at the closest location on the target, which is our line, and they will form a stitch connection there. Okay, so for this point, what is the closest location on our line? This. So it will just form a stitch connection, and similar to that, all our Vellum cloth objects will do the same thing. Okay, so I hope you understand that we are applying our Vellum stitch points to our points here, the cloth points here. Okay, and then we are setting the target on the line. Okay, and we are basically saying, by turning on the use closest location on primitive, that for the points on the Vellum cloth geometry, they need to find the closest distance on the line geometry and then just create a stitch network there. Okay, and you can use the maximum distance here of the stitch. So by default, I've used 13.97 to something like that. If you want to play with this, you can obviously play this. Okay, so this is what we are getting. We have stitched together the Vellum cloth, these points here, these points of the Vellum cloths, to our target, which is the line. Okay, and they are looking for the closest location or the closest position on our target and just forming a stitch there. Okay, so this is really nice. And now what we can do is we can attach it with our Vellum solver. So now that we have connected our Vellum stitch to our Vellum solver, if I play this, this is what we are gonna get. If I just untemplate this, this is what we are getting. Okay, our rope here or our line here is behaving just like we wanted, just like a rope, because we have given our hair constraint to it, and then the cloth geometries are behaving like cloth here. Okay, and they are attached together with the help of our Vellum stitch points. So you use Vellum stitch points when you want to attach two different Vellum geometries, okay, Vellum objects. So this is a good option here to connect two different kinds of Vellum objects. There's one more, which is the glue constraint. We will look at that as well, but this is our Vellum stitch points constraint. Now after the simulation, what I can do is I can use a split here, and I have split both the line, which is this, and our cloth geometry, which is this. Okay, and I have given a name attribute to every single one of these clothes objects, and then I have colored them, and this is what we are getting eventually. Okay, so I hope you understand this. The Vellum stitch is basically used to stitch two different Vellum objects, and we can also use our spear or our balloon and any other kind of Vellum objects. Okay, so this is it. Okay, so now we are going to cover one of the most interesting constraint in Houdini, which is the pin to target constraint. And we already know how to pin certain points in an object, in a Vellum object, so that they do not participate in a simulation. But pin to target constraint is a little different. Okay, as you can see in this, we have a Vellum object which is rotating, but it is also getting simulated. As you can see, it is animated, but it is also interacting with the colliders here as a balloon object. Okay, so this is a mix of both animation. If you get an object which is animated and you want to simulate it also as a Vellum cloth or as a Vellum balloon or anything else, then how would you do that? This is what we are going to learn in this chapter. Okay, so I'll just show you one more time. This is an animated object, but I wanted this object to behave like a balloon. So as you can see, it is rotating because it is animated, but when it is colliding with these objects, with the colliders, it's also behaving like balloon. Okay, and in this way we are mixing both the animation and our Vellum simulation. So let's see this, how I did it. So I have an object here which is our tube. Okay, so what I have done basically here is I have taken a tube. These are the settings. I have rotated it in this axis. The rows and columns are this, and what I've done here is I've used a polyfill node. Okay, and after the polyfill node, I've used a subdivide here. I'll just show you the smooth batch shaded. So I subdivided this tube now. Okay, and I have created another version of this, but I have rotated it 90 degrees and then I merged both of them, and now we are getting an object which is something like this. But as you can see, they are not properly merged together, so I've used a VDB from Polygon. So these were our two objects, okay, but I wanted this to look like one object. To merge them properly, I have converted them to VDB with the help of this node called VDB from Polygon. So now this is VDB, okay, and I have changed the voxel size. I have kept it low so that there's enough detail here, and after that I have used a convert VDB. So basically what I'm doing with the help of this convert VDB is I have reconverted that VDB, this VDB, back to polygon. Okay, so we had geometry here, polygonal geometry here, okay, then I wanted to merge them together properly, so I have converted them to VDB, okay, and after converting them to VDB, I wanted this VDB to convert back to polygon, so I've used a convert to VDB here, and I've converted that VDB into polygon. Okay, after that I wanted this to have triangulated high resolution geometry, so that's why I've used a remesh node here, and in this remesh node I've changed the target size to 0.025 so that we have enough geometry for our simulation. You can see there are 10,000 points almost, which is nice. And after that I've used a transform node, so I have moved the object here up a bit in the y-axis by 0.3 meters, and then I have rotated it. I have done some animation here so that it is rotating in the y-axis, continuously rotating in the y-axis. Okay, so this is our basic geometry. This is our animated geometry. As you can see, this is our animated geometry. And now let's see that some different artist has given me this animated geometry. He has told me that listen, this is the animated object that I'm providing you, and what I basically want is I want you to simulate it like a balloon, but that balloon should be rotating as well. So far what we have seen is that we have created an object, okay, and then we do the Vellum configuration, and then we connect a Vellum solver here, but it will just behave like a balloon. It will fall down probably on a ground, and it will inflate or deflate, and we can do all of these things. But to combine both the animation and simulation, to control our Vellum object in a way that it is not only following its original position, which is the animation, it is not only following its animation, but it's also getting simulated like a balloon. We haven't done that, and we will do this now. Okay, so this is our animated geometry, and now we will simulate it with the help of three constants. One is the Vellum Balloon configuration. So Vellum Balloon configuration has two constants, which is the cloth constraint and the balloon constraint, the pressure constant. And the next constant that we will be using is pin to target constant. Okay, so first we will use a Vellum Balloon configuration. So basically what I did here was I used a Vellum Balloon configure. Okay, so this is what we got. I connected it here, and what I'm going to do is I'll just copy this Vellum solver. Okay, and I connected our Vellum solver to our Vellum Balloon configuration. And in the Vellum solver, what I've done here basically is I have changed the substeps to 4, okay, so that the calculation is more accurate. Our solver is calculating this simulation 4 times per frame. That's what we are doing here. And then I turned on the ground plane. So if I just use our normal default Vellum Balloon configuration without any setting changes and with the Vellum solver, let's see what we are getting. Okay, so this is what we are getting. This object is behaving like a balloon, but there's not enough pressure inside it, so we can do some changes here, setting changes here. So I'll come to the Vellum cloth, and you can see that in the stretch section the stiffness is very low, so I'll just increase it, okay, so that it doesn't stretch that much. I have kept the stretch stiffness in the Vellum Cloth Constraint very high. The stretch section, as I have already told you, that the stretch section controls how stretchy the cloth object is going to be, and the bend section controls how bendy or foldable the cloth object is going to be. Okay, we are not going to change anything in the bend section. Then I'll come to the pressure here, and in the pressure constraint there's only stretch section here. Okay, and I have already told you that the stretch section maintains the amount of pressure and controls how much pressure is generated inside this object. Okay, so with the help of this stretch stiffness, we controls or we maintains the pressure inside our geometry here, inside our object. So I'll just keep it at very high, 1e plus 10, and the rest length scale controls how much pressure is generated, controls the amount of pressure. So if I increase it, more pressure will be generated here, but we do not want to change anything regarding the amount of pressure. Okay, so I'll just keep it at default 1. Now if I play this, now you will see that it is behaving better. Okay, it's behaving like an inflated balloon object. It's falling down on the ground. But one thing that is happening here is that it's not rotating. Okay, so we already know that we can make sure that any point here of the vellum object, any part of the vellum object, we can make sure that it doesn't take participation in the simulation. It follows its animation. Okay, and we can do that with the help of the pin to animation. So if I pin all the points here, okay, they will all follow the animation. Okay, so if I just press star, and star here means everything. Okay, all the points here, all the geometry here is considered to be pinpoints. So I pressed star here, and if I play this, let's see if anything happens. Now you will see that this object doesn't even fall on the surface, but it's not following the animation as well. So to change that, we need to turn on this match animation here. Okay, so if you want any of the pinned object to pinned points to match its animation, follow its original animation, you have to turn this on. Okay, so we have turned this on. Now if I press this, this is what we are getting. Okay, so this object is now following its original position, just like our main geometry here. There's no difference between this and the result that we are getting after our simulation. They both are same. Okay, there's no effect of our Vellum Cloth Constraint, or there's no effect of any of the properties that we are providing, the bendable properties, the folding property, or the stretchy property, or the pressure that we are creating here. None of that is taking effect. Okay, and it's pretty confusing. So if I come to the Vellum cloth, come to the pin to animation, and if I deselect anything, okay, if I turn it off completely, and if I play this will behave like a balloon, but it will fall down. It's not following the animation. If I use all the points here for the pin to animation, okay, if I use all those points, all the geometry or the vellum geometry is rotating. It's following its animation, it's matching its animation, but it's not at all, inflating or deflating, or there's no kind of simulation here. We want to do a combination of both, and we want to do a proper merge of both the conditions. We want this to behave like a balloon, and we want it to also follow its animated path. Okay, so how can we do that? We can do that with the help of another constraint, which is, we will have to create a Vellum constraint node here, Vellum constraint, and then we will connect it here between the Vellum solver and our Vellum pressure, and we will call another constraint. So change the constraint type to pin to target. Okay, this is our pin to target constraint. What this does is it helps us in maintaining a balance between the simulation and the original animation. Okay, so with the help of this constraint, what we can do is we can ask our geometry, our vellum object here, to not only follow the animation path but also participate in the simulation, also behave like a balloon. Okay, and how can we do that? So if you come to the vellum constraint, we will come to the pin to animation here. Okay, and we will change the pin type from permanent to soft. Okay, if I change it to stopped, nothing will happen. All of the geometry will not participate in the simulation. It will just stay like this only. Okay, it will follow the animation, but it will not do any kind of simulation here. Okay, so this is the thing that we are getting. Which we also got while we put a star here. So actually I have also turned on the star here. We will just remove everything, any conditions from here, from the Vellum Cloth Constraint. Okay, don't keep any points here in the pin to animation while we are using pin to target here. Okay, so now if I play this, you will see that pin type is stopped and everything is stopped. This is neither creating any motion animation, it's not simulating also. So this is one of the pin type. The other pin type that we are going to use is a soft. Okay, so change the pin type in the pin to target constraint as soft. Okay, and what this soft pin to animation constraint or the pin to target constraint will help us do is the thing that we want, which is the combination or the merge of both the conditions, some kind of animation, the original animation, and the behavior of balloon. Okay, so what I'm gonna do is I'll change the pin type to soft and then turn on the match animation. Okay, so now if I play this, let's see what we're gonna get. So this is following the animation now, but to see its proper effect, what I'm gonna do is I'll connect these geometries that I have created as a collider to our simulation. Okay, so I'll connect it here, and if I play this, let's see what we get. You will see that our object is behaving as an animated object. Okay, so it is following its animated path, and you can see some kind of cloth like behavior here, not the correct behavior but some kind of behavior. Okay, so we are halfway there. At least it is interacting with our objects here, our colliders here. It is behaving, at least it is simulating. Okay, which was not happening before. Now that it is simulating, we need to only play with our settings. So I'll come to the Vellum constraint and I'll tell you what the stretch section and the bend section controls in the Vellum pin to target constraint. This stretch stiffness is the thing, and in the bend section, the bend stiffness is the main thing. This stretch stiffness and the bend stiffness is like a balancer. Okay, if the stretch stiffness is very high, keep in mind what I'm saying. Okay, if the stretch stiffness in pin to target constraint is very high, then this object will highly behave like a animated object. So we have two things here. I'll just write it. We have animation and then we have simulation. Okay, if the stretch stiffness is very high, then the object will follow its original animation position. Okay, and if the stretch stiffness is very low, then the object will perform as a simulated object. Okay, so this stretch stiffness is behaving like a balancer or behaving like a lever here. Okay, if the stretch stiffness is very high, it will give priority to animation. Okay, I'll just write it here. Stretch stiffness very high means priority to animation. Okay, and stretch stiffness very low means priority to simulation. Okay, so this is basically what is happening here. This stretch stiffness is behaving like a balancer or behaving like a lever. Okay, so you basically controls how the vellum object is going to behave, or what the vellum object is going to give priority to. Is it going to give priority to its animation, its original animation, or is it going to give priority to its simulation? So currently the stretch stiffness is very high. Okay, so now you will see that it is behaving like an animated object. It is following its animated path perfectly, but we are getting these kind of effects here, which we do not want. It's not behaving, it's not properly simulating. Okay, because we have set the priority as priority to our animation by keeping the stretch stiffness very high. If I keep the stretch stiffness very low, let's see what happens then. You will see that it just falls down and there's no animation here. Okay, if the stretch stiffness is very high, it gives priority to animation. If the stretch stiffness is very low, it gives priority to simulation. Okay, currently it is giving priority to simulation because the stretch stiffness is very low. We need to play with this value. We need to find the optimal value where our object, our vellum object, will combine both the powers. It will not only behave like a simulated, it will not only follow its animation path, but it will also behave like a simulated object. So let's keep it somewhere in the middle. If the stretch stiffness is 1, let's see what we are getting. You will see that as soon as the the simulation begins, the object here has fallen down and it is also trying to follow its animated path. It is trying to move here. Okay, it's not behaving correctly. We are not getting the result that we want, but somewhere in the middle, when the value is somewhere in the middle, it is doing some kind of balance here. Okay, so if I play with this value one more level, if I increase the stretch stiffness to maybe 100, let's see if we are getting a correct result. Okay, so now you will see that not only the object is following its animation path, but it's also reacting to this colliders and behaving like a balloon. Okay, so it's bending like this, there's pressure here, and then suddenly it's just moving that way. It's behaving like a balloon. That's what we wanted. So in my original, the values that I've set here, you will see, if you come to the Vellum constant, is I kept the stretch stiffness in the pin to target constant to around 100, which is okay, the same as that I've used here. But the bend stiffness here is 0.01. Okay, so I wanted it to bend a little more, and when it is doing the bend, I wanted it to give a little more priority to our simulation. Okay, so if I run this now, you will see that the object is moving and it is also behaving like balloon. So this thing is happening at both the places here. The stretch stiffness controls what we are giving priority to. If the stretch stiffness is very high, then it will give priority to animation, and if the stretch stiffness is very low, it will give priority to simulation. Similarly, with the bend stiffness here, if the bend stiffness is very high, it will give priority to animation, and if the bend stiffness is very low, it will give priority to our simulation. So you need to find the optimum value here, okay? And the other thing that I've used here, if we come here and if I give the same value here to the bend, if I run this, we will get the same result almost, okay? But there's one thing that I've changed here, which I'll just show you now. Okay, so if you will see, after it's getting freed here, there's some kind of jerk here, okay, which is normal. But we can try to reduce this jerk or this kind of jerky movement here by playing with the damping ratio, okay? So what is this damping ratio? Basically, the damping ratio here, let's read what is. Stiff constant into damping reduces this by bleeding energy when evaluating the constant. Too much damping can prevent the constant from being satisfied. However, values less than 1 must be used. So in simple words, I'll just tell you, damping tries to bring the object which is in motion or which is in simulation, it tries to bring to its original condition or original position. It tries to bring it to its original position, which is the static value, okay? If the object is moving too much in the simulation like this, if we increase the damping ratio, it will try to bring down this object to static motion, okay? So we can try to bring down this jerk motion to some kind of static value, okay? We will try to stop it as soon as the time progress, okay? So I can increase the damping ratio here by 0.01. I'll come to the pressure also. I'll increase the damping ratio here as well, and I'll come to the Vellum Cloth Constraint and I'll increase the damping ratio here as well. So basically, damping ratio tries to calm down the simulated object. If it is moving very quickly or it is jerking like this, it basically says, damping ratio basically says, hey, calm down, don't jerk too much, try to maintain your position or try to maintain your shape, okay? Don't move too much. That's what it's trying to do. So let's see if we are getting some kind of good result here. Okay, so I am satisfied with this, and I hope you understand what this Vellum pen to target constant does. With the help of the Vellum pen to target constant, what we can basically do is we can try to combine both the animation and the simulation in a better way, okay? If the stretch stiffness, as I said already, if the stretch stiffness is very high, then it gives priority to our animation. And if the stretch stiffness is very low, it gives priority to simulation. And if we can find the optimal value somewhere in between, then both will happen. It will follow the animation path and it will also behave or simulate, okay? So after the simulation, what I've done here is I've used a Vellum post process. I've not changed anything here, just colored here, and I have merged both the colliders and our Vellum object, okay? So if you have any doubts here, just let me know and I'll try to solve it. Okay, so there are two more methods in Houdini Vellum when we talk about soft body simulation, and one is this, the Struts method, where we create the constant type which is struts, and the other method is by creating Vellum Tetrahedral. So along with the Vellum Balloon configuration, we also have Vellum Struts configuration and Vellum Tetrahedral configuration for our soft bodies. So I'll just show you what it is. So this is our geometry. Okay, this is our geometry and we want this to behave like a soft body, like an organic body. Okay, so when it falls, we want some kind of soft body simulations on this. So there are two methods, as I said. The one method is the struts method. So let's look at this first. To create this, we have a geometry and we want this to behave like a soft body. So we'll just create Vellum strut configure. Okay, and when you create this, you will get these two nodes. The one is the Vellum cloth node, which obviously converts the object into a cloth. It asks the object to behave like a cloth by giving it two important properties, as we have discussed earlier, the stretch property and the bend property. And other than the cloth configuration, other than the cloth constant, we also have the Vellum strut constraints here. Okay, and we will see what all both of them are. You already know what the Vellum cloth constant is, so I'll just connect it with our object here. Okay, so once I have done that, you will see that our object will have some kind of constants here. So if we just disconnect the Vellum cloth constant, and we will just visualize our Vellum strut constant. So let's see what it is. I'll just use a null here to visualize this properly, and you will see that these strut constraints are basically primitives, or you can say these are basically lines which are filling up, these constants are filling up the volume of our object here. Okay, so if we look at our object here, this is our object, and when we have applied our strut constant, you will see this part is filled with constants, the strut constants, to fill up the volume. Okay, so this is what we are getting. And if you want to imagine, we can actually look at a sphere here to understand it better. This is a sphere. I just connect it here, and if we look at it, this sphere, and if we look at the strut constant that it is creating, this is what we are getting. Okay, so these strut constants are organized in a fashion in our in the volume of our geometry, so that they maintain the volume, they fill the volume of this geometry. Okay, just look at this. So if I think of a ball which is filled by these kind of structures, if we drop it, then it will obviously maintain the volume of that ball structure. Okay, so we'll just use our original geometry here. So basically these are the constants, struts constant, which are filling up the volume of this object. Okay, so if I use our Vellum solver with them, so these needs to be connected. So we will use Vellum cloth constant with combination of Vellum strut constant to get our results. And you already know how Vellum cloth constant works. We have stretch section and bend section, and by default when we are creating the strut configuration, the stiffness is very high and the bend is somewhere in the middle, 0.1. Okay, if we come to the struts, you will see that there's not many settings here. Okay, the two things that we are getting, I'll just disconnect it again. The two things that we are getting in our strut configuration is, first is strut search, which is, and it has a it has a value here which is called max strut length. So basically these strut constraints, we are asking them to search or create struts in a length in an area which is about 100 meters. So if the object is greater than 100 meters, it is larger than 100 meters, then we will have to adjust our value here. Okay, so this will always work. You don't really need to change it because most of the time our objects are not going to be bigger than 100 meters. But if you have an object bigger than that, then you will have to play with the values here. Okay, the other thing that is interesting is, look at the constants here. We can change, and all these constants are forming a connection between two different points. Okay, so here we have decided that per constant per point, so each point is only going to get connected to another point, so we can only create one constant per point. But if I increase it to 2, you will see that the number of constant will increase. See, this is what we are getting when we have kept it at constant per point, one constant per point. If we increase it, then the constants per point, which means one point can produce this many constant. Okay, so I'll just keep it at 1, it's all right. And then we have our stretch stiffness here, okay, or stretch section here, and this works similar to our other stretch sections. This basically just controls how strong the constants, the strut constants actually are. If the stretch stiffness is very high, they will be very strong. Okay, they will be able to maintain the volume. If you push this object, then these constants will be able to they will not crush, they will not crunch. Okay, they will be able to hold the volume, they will be able to hold the pressure out from outside, they will not crunch. Okay, so I kept the stretch stiffness as 1e plus 10, and which is, I think, quite nice. Now if I connect it to our Vellum solver, in our Vellum solver I kept the substeps to 4 because I think we will need a high substep amount for our calculation in this one, and I turned on the ground position. Now if I play this is what I'm getting. So it basically behaves like a soft body, like a jelly like substance. Okay, it's not behaving like a balloon at all. So think of it like a, yeah, jelly is, I think, a good example. Or you can think of meat. What about meat? So when you get chicken breast or anything, something like that, if you throw it on a table or if you just throw it on your kitchen desk, it will have some kind of soft body behavior. So this is quite similar to that. Okay, so this was what Vellum strut constant is, and now we can look at our Vellum tetrahedral configuration. Okay, so now if you want to look at the third method for soft body simulations in Houdini Vellum, it's the tetrahedral method, because we are going to use a tetrahedral Vellum configuration. Okay, so this is our geometry, and what I'm going to do is I'll create a Vellum tetrahedral soft body configuration. Okay, and what this is going to do is it's going to create two nodes here. One is tet conform, okay, and the other is Vellum tetrahedral configuration. And you will notice that this is one of the Vellum configuration where we do not need our cloth constant. Okay, our base constant, which is the cloth constant, is not needed here. And what is happening here basically is, this is our geometry, and what we are doing with our tetrahedral configuration is we are filling this geometry with small pieces of other geometry. So small pieces of triangles basically. So if I select this constant, if I look at this, okay, and if I use a delete node to show you, this is a delete node. I'll use a bounding box. Okay, And if I move this bounding box, you will see that this object is not empty. Okay, it's not hollow. It's actually made up of small tetrahedrons, okay, which are actually, if I just select this one, okay, anyway, so this geometry is filled with a small tetrahedron geometry. Okay, it is not hollow. It has been filled up with the help of our Vellum tetrahedral configuration, and there are not many options here, to be honest. While this is one of the most accurate when it comes to soft body simulations, it behaves like a soft body. So while it is one of the best options to do our soft body simulations in Houdini, I don't really use it that much because it doesn't really give too much control to us. Okay, so we have a stretch section here. If you come to the constant tetrahedral, if you come here, you will see that we have our geometry section, we have density, mass, and all of the default things. Then if you come to the stretch section, we have our stretch stiffness. So this basically controls how rigid or how soft our body is going to be. If it is very low, the stretch stiffness is low, it's going to behave it's going to be too soft. Okay, and if it is very high, then it's going to have some kind of rigidity. It's not going to be so soft. So I'll just connect it here. I have already connected it here. I have not changed any default settings here. I'll kept the stiffness to 1e plus 10, and if you look at this when it is falling down, this is what we are getting. The object is behaving like a soft body. So if I decrease the stretch stiffness, if I play this again, this is what we are getting. Okay, it's too soft. We need to make it quite rigid here. Okay, and that's how we will be able to control how soft this is going to be. So this is one of the three methods. I have already shown you the Vellum balloon configuration, which I use most of the times. The Vellum cloth and struts give you a little more control than our tetrahedral configuration here. So you can choose whatever you want for your projects. I would suggest that first try with Vellum balloon configuration, try to play with the values there, but if it is not pressure based, then I think you can try with our Vellum struts, and this will get you most of the results that you're looking for. And the tetrahedral configuration is also very powerful, very nice, and it gives you very beautiful results, but the only thing is that there's not that many changes or that many control that you get with this. Okay, so I hope you understand these basic, not so basic, but simple Vellum configurations that we can use for our soft body other than Vellum. Hi guys, so if you want to learn more about Vellum or Flip or particles or any other tutorials, then consider joining my course, which is called Houdini Supremacy, and you'll get access to all of my videos here. The link will be in the description if you are interested.